Hi everyone, welcome back. So in the last lecture we were looking at some graph, right? So with respect to conductivity, carrier concentration and mobility versus temperature graph we have made. Along with that, mobility and conductivity versus doping concentration graph also we have made. Now another expression we studied, what that was? Drift velocity versus electric field. So what we studied, that your drift velocity is proportional to electric field. And when you remove this proportionality sign, what do you get? Mobility. So this expression we have already studied, right? Vd is equals to mu e and Vd is proportional to E. What does that mean? That means between Vd and E, there should be a straight line. Between Vd and E, there should be a straight line, and since mu is a proportionality constant, so mu should be constant. But your happiness will stop here, because initially when you give more electric field, let's just say this was your semiconductor, and there was an electron. We are talking with respect to electron, so we will be talking about the drift velocity of the electron. So if I give more electric field, if I was increasing the voltage here, if I am increasing the voltage, what does that mean? Electric field will also increase. Why is that so? Because E is equals to dV by dx, or you can call it V by L, right? If the length is L. So if V is increasing, electric field will also increase. All these formula we have already seen, right? So if voltage is increasing, then electric field is also increasing. If electric field is increasing, that means what is the force? F equals to QE. That means this electron is going through more force, because electric field increases, then force increases. So in this opposite direction, this electron is feeling more force, and if it is feeling more force, what does that mean? Its velocity will be more, right? Because if electron is feeling more force, then its velocity will be more. It will generate more velocity. So yes, with the increase in electric field, that means with the increase in voltage, your velocity of the electron will increase. Your drift velocity of the electron will increase, right? And it will increase proportionality. Vd is proportional to E. In that manner, it will increase. But since electric field increases, what will happen? More and more electric field means more and more velocity. But there is some scattering, because this electron is not free. There are silicon atoms. If your electron is gaining more energy means voltage is more, electric field is more, force is more. If force is more, that means energy is more. So if your electron gets more energy, then what will happen is that it will try to accelerate faster. So if it tries to accelerate faster, what will happen is that there are silicon atoms. Now this electron will collide through these silicon atoms. So eventually it tried to go linearly, although velocity will increase only, because you are increasing the electric field. Although the velocity will increase only, but it will increase slowly now, because the scattering has increased. Are you able to understand this point? So it will increase slowly. In that manner it will increase. And if you just keep on increasing the electric field, at some time the velocity will saturate. So velocity will say that I cannot increase beyond a certain limit. Like, it's not that, sir, velocity will reach infinity. Velocity cannot reach infinity. Velocity will not keep on increasing, because as you apply more and more electric field, more and more collisions will happen, and more collision will happen. That means what will happen is that your velocity tried to increase so much faster, but it was not able to increase so much faster, because actually this mobility is going down. Why mobility is going down? Because scattering is increasing. If electron is trying to move faster, scattering will increase, so mobility will go down. So although this part is increasing, electric field is increasing, but mobility is going down. So what will happen is that slowly it will increase, but it will increase slowly only, and after some time it will saturate. So Vd will increase, then increasing slowly, and after some time it will saturate. So till this particular point, it was rising linearly. Till this particular point, it was rising linearly. After that, what really happened was, it was rising in under root manner. Basically, here Vd was proportional to E. What I would say, here Vd was proportional to E. Here Vd became proportional to under root E. And here Vd became proportional to, I would write down E in the other manner. So here Vd was proportional to e to the power 1. I would call it e to the power 1. And here Vd was proportional to e to the power half. And here your Vd is proportional to e to the power 0. Why e to the power 0? That means with the increasing E, there is no effect in the drift velocity. Even if your E is increasing, even if your E increases, Vd remains constant. So slowly your drift velocity will saturate. Is that clear to you? So in the first scenario, Vd is proportional to E. What I am saying, Vd is proportional to E. Vd is proportional to E. So mu will be constant. Mu will be constant. In the second scenario, Vd is proportional to e to the power 1 by 2. Then mu, what will be the relation between mu and electric field? What I am saying, Vd is equals to mu E. Vd is equals to mu E. In this particular region, I am saying that Vd is proportional to e to the power 1 by 2. So Vd is proportional to e to the power 1 by 2. When I remove the proportionality sign, I am taking one constant, that is k. So Vd is proportional to e to the power 1 by 2. That would be mu E. So this is e to the power 1, this is e to the power minus 1 by 2. So what you are getting? Sorry, this is e to the power 1 by 2 and this is e to the power 1. So what you are getting? E to the power minus 1 by 2. So mu is equals to k into e to the power minus 1 by 2. So mu is proportional to e to the power minus 1 by 2. So basically mu will decrease. Mu will decrease. In what manner it will decrease? It will decrease in this manner. So here your mu was not depending on electric field. So mu was proportional to e to the power 0. But now your mu is proportional to e to the power minus 1 by 2. And here what is happening? Vd is proportional to e to the power 0. So what is the expression? This is the expression. Vd is proportional to e to the power 0. So if you remove the proportionality sign, some constant will come. Mu is equals to e. E to the power 0 is 1 only. So basically you can say that Vd is constant. So if Vd is constant, that means it is some constant value. So what you can see? Mu is equals to k by e. So mu is equals to k e to the power minus 1. So you can say that mu is proportional to e to the power minus 1. So after that mu will keep on decaying because scattering is increasing. If scattering increases, then mu will keep on decaying. So now mu will become proportional to e to the power minus 1. And here, if we write down with respect to Vd, then how we will write down? So first Vd was proportional to E, then Vd became proportional to e to the power 1 by 2, and then Vd became proportional to e to the power 1 by 2, and then Vd became proportional to e to the power 0. So 1 by 2 0, 0 minus 1 by 2 minus 1. So this graph will be very easy to remember. Vd versus E graph. Vd first it will rise linearly, but after some time what will happen is that scattering will increase, so it will rise sublinearly. What this is known as? This was your linear region. Okay, linear region. This is known as sublinear. Sublinear. It tried to become linear, but now it is increasing slowly, not in a linear manner. Because if it was linear, then it would have gone somewhat like this. But now it is not going somewhat like this. It is going in the slower manner. So slower manner means Vd is proportional to e to the power 1 by 2, and this is known as saturation. This region is known as saturation. So this graph is very important. Okay, very important graph to understand any IV characteristics. So IV characteristics also we will discuss. So any particular device that you are having, whether it is a semiconductor, it is diode, MOSFET, VGT, any kind of device that you are having, without this particular graph, you cannot understand any device. For understanding any device, you need to know this particular graph. So you remember the logic or not, I don't care. What is the logic? That first it will rise linearly, then scattering will increase, mobility will decrease. Even if you forget this logic, it is fine, but the nature of graph should be clear. Rises linearly, then sublinear, and then constant. Whatever the logic is there, after 5 days you will forget it. If you don't revise it, then after 5 days you are going to forget the region. That what was the actual region, why it was rising linearly, then sublinearly, and then saturate. You will forget the region, scattering and everything you will forget. But the nature should be clear to you, that how the graph will rise, linear, sublinear, and then saturate. So that nature you are not going to forget. Okay, what was the reasoning, what was the theory, all this theory will be written and you will be forgetting it. I know that. Okay, I have also been a student. If you don't revise EDC, then all this theory you will forget. But this waveform you are not going to forget. You cannot forget the waveform. Okay, and reasoning also is clear. What is the reasoning? The only reasoning is that if you keep on increasing the electric field, that means electron will feel more force. If they are feeling more force, they will try to accelerate very faster, and if they try to accelerate very faster, they will scatter more, and since they are scattering more, so mobility will decrease. So if in the initial manner mobility was constant, but since your electron tried to go very fast, your mobility started decreasing. Although electric field is increasing, but mobility is decreasing. So now initially it was rising linearly, but now it will rise sublinearly, and eventually what will happen is that electron will gain so much of energy that mobility will start decreasing so much. So eventually your velocity will saturate. So increase, sublinear, and then saturate. A very, very important graph, and all the reasoning and everything have been written here. Okay, so this graph, when you are making this graph in your notebook, just make sure that you make it in a very good manner. Now let's write down the typical values. So this value is for silicon, this is roughly around 10 to the power 3 volt per centimeter. You don't need to mug it up. Okay, if you can remember, you can remember, but no need to mug up. If some question is coming, they will give this data, and this value is roughly around 10 to the power 4 volt per cell. 10 to the power 4 volt per centimeter. Okay, so when your electric field is 10 to the power 3 volt per centimeter, till that point it is rising linearly. When it is between 10 to the power 3 to 10 to the power 4 volt per centimeter, at that time it is rising sublinearly. And when your velocity becomes, when your electric field becomes 10 to the power 4 volt per centimeter, after that it will saturate. Okay, and another thing is that this velocity is 10 to the power 7. As far as I remember, it was 10 to the power 7 only, right? 10 to the power 7. So this saturation velocity is, for silicon it is 10 to the power 7 centimeter per second. Again, you don't need to mug it up. These values, even if you forget, no need to worry about that. But the nature should be clear. Vd is proportional to e to the power 1, e to the power half, e to the power 0. If you are able to write down this one, then surely you will be able to write down this one as well. All good, all fine. Let's read out the theory. You can read the theory on your own. In silicon at a low electric field, the drift velocity of carrier increases linearly with the applied electric field according to Vd is equals to mu e, where mu is constant. Mobility remains nearly constant in this region. As the field increases beyond 10 to the power 3 volt per centimeter, carrier will gain higher kinetic energy because between the collision and undergo more frequent scattering with the lattice through optical phonon emission. Now you are not able to understand this optical phonon emission. What is the meaning of this optical phonon emission? You will just understand that it is nothing but lattice scattering. Okay, optical phonon emission means it is nothing but a lattice scattering. So there will be more and more lattice scattering. Okay, because electrons are trying to move fast, but atoms are vibrating. Since they are vibrating, they will collide. If they are colliding more, then mobility will decrease. So this is what has been written. This enhanced scattering effectively reduces the mobility. So drift velocity is no longer rising linearly, but instead it will rise more slowly, approximately proportional to under root E. When the field is reaching above 10 to the power 4 volt per centimeter, the scattering rate will become so strong that additional energy means even if you are increasing the electric field, even if you are increasing the potential, the field is quickly dissipated to the lattice via phonon emission. That means there is no effect of the increasing of the field. So what will happen is that there is no further acceleration. As a result, the drift velocity will be saturating at nearly constant value of 10 to the power 7 centimeter per second, known as the saturation velocity. Okay, so this is the complete theory that has been written. So this graph is clear to you, Vd versus E graph. All good, all fine. Let's solve some question. So for a silicon semiconductor, electric field is changing from 4000 volt per centimeter to 8000 volt per centimeter. The mobility of electron will be multiplied with the factor of what? Silicon is given. Electric field is changing from 4000 to 8000. So when your electric field is between 10 to the power 3 volt per centimeter to 10 to the power 4 volt per centimeter, right? Although data should be given in the examination, data would be given, but all these data I have written for silicon, so I asked the question on silicon only. So here I did not give the data, but in the examination they will give the data that in this particular region the electric field is rising sublinearly. What does that mean? That your mobility will be e to the power minus half. Say yes or no, right? Your mobility will be proportional to e to the power minus half, right? In this region, mobility will be proportional to e to the power minus half. So now what they are saying, electric field is changing from 4000 to 8000. So mobility of electron will be multiplied with what factor? So your mu two is the later on mobility. Basically, when electric field is 4000 volt per centimeter, at that time your mobility is mu1. When your electric field is, this I will call E1, this I will call E2. When your electric field is 8000 volt per centimeter, at that time your mobility is mu2. Your mobility of electron will be multiplied with what factor? So what I will find out? Mu2 by mu1. That will be equivalent to E2 to the power minus 1 by 2 divided by E1 to the power minus 1 by 2. So that can be written as under root E1 by E2, because this is 1 by under root E1 and this is 1 by under root E2. So E1 will go upward, E2 will go downward. So mu2 by mu1 is coming out to be under root initially 4000 divided by 8000. So what we are getting, 1 by 2, 1 by under root 2. So mu2 is mu1 by under root 2. So this is the answer. So basically your mobility is multiplied with the factor of 1 by under root 2. Your mobility is multiplied with the factor of 1 by under root 2. That would be the answer. All good? All fine? Very easy question. Although this data should have been given, but since we have wrote down the data for silicon only, so I use this data here directly. Let's solve more questions. A DC volt of 10 volt is applied across a N-type silicon bar having a rectangular cross-section area. Having a rectangular cross-section. Length is 1 centimeter shown in the figure. The donor doping concentration is Nd and mobility is given. Find the average time taken by electrons to move from one end to the other end. What you need to find? Time you need to find. Average time from here to here. What is time? Time is equals to speed upon distance. Oh, sorry. अरे भाई, I am a Hindi medium student. Distance upon speed. Time is equals to distance upon speed. Like very, very disappointing, right? I have to write down the formula. Time is equals to distance upon speed, or you can call it velocity. So you know that the electron, if the electron is going from here to here, it needs to cover the distance of 1 centimeter. But you need the velocity. So can you find out what you need to find? Average time. So distance upon average velocity. So can you find out the average velocity? Yes. What is average velocity? Average velocity is Vd. What is the formula of Vd? You know. Vd is equals to mu e. This is the only formula we know. Mu we are having. Do we have electric field as well? Yes. Because what is the potential? 10 volt. What is the length? 1 centimeter. So what will be the electric field? V by L. I told you. Across, what is electric field? Electric field is minus dV by dx, right? Minus dV by dx. So let's just say this is your x equals to 0 and this is your x equals to L. So when you are going from x equals to 0 to L, how much your voltage is changing? From 10 to 0. And you are going from 0 to L. So minus L you will put here. So 10 by L, right? So 10 by 1 centimeter. 10 by 1 centimeter. So 10 volt per centimeter. This is your electric field. Okay, and are you having the value of mobility as well? Yes, mobility value is also there. So what will be your Vd? Vd will be, mobility is also given in centimeter square, electric field is also in centimeter square only. So mobility is 10 to the power 3 into 10. And what will be the unit? Meter per second, centimeter per second, right? So what you are getting? 10 to the power 4 centimeter per second. This is your drift velocity. So here what you will do? 1 by centimeter upon 10 to the power 4 centimeter per second. So what is the answer you are getting? 10 to the power minus 4 seconds. This is the average time. This is the time taken. Microsecond they are asking. So in microsecond what it would be? Your answer is 10 to the power minus 4, right? So in microsecond can you convert it? Yes, I will multiply by 100 and divide by 100. So what I will be getting? 100 microsecond. Because if I multiply by 10 to the power minus 2, I will have to divide by 10 to the power minus 2 as well. So 1 by 10 to the power minus 2 will become 100 and 10 to the power minus 6 will become micro. Answer is 100 microseconds. So this will be the answer. Very, very simple question. In the EDC, always you just see that, sir, what we need to find. We need to find the time. Time is distance upon speed. Distance I already know. This is not the collision time. Don't feel like collision time or anything. No, nothing is there. Collision time, all these things are not there. Collision time is a separate, different thing. What they are asking, they are just asking that average time taken by the electron to reach from one end to the other end. So distance is 1 centimeter divided by the drift velocity. Drift velocity will be mu e. What is the value of mu? Mu value is 10 to the power 3. What is the value of electric field? That is 10 centimeter per second, right? So 10 to the power 4, and then then I put it, I get the value of 100 microsecond. Let's solve next question. You try doing it on your own, you will be able to do it. A piece of silicon is doped uniformly with phosphorus with donor concentration of 10 to the power 16. Donor concentration is given as 10 to the power 16. The expected variation of mobility versus the donor concentration is given. I told you, mobility versus donor concentration. As the donor concentration increases, the mobility decreases. So yeah, this is happening. So the graph for electron is also given, the graph for hole is also given. Now what they are saying, assuming full dopant ionization at 300 Kelvin, the graph is given. Using this data, determine the approximate value of mobility mu n at Nd 10 to the power 16. Okay. When your Nd is 10 to the power 16, 1 e plus 16, what is the meaning of that? 10 to the power 16 only. Okay, this is your 10 to the power 16. When your Nd is, when your doping concentration is 10 to the power 16, at that time, what is the value of mobility? The value of mobility is 1200, 4 electrons, and 4 holes, it is 400. Okay. And calculate the conductivity sigma of the silicon crystal. Assume electrons are the majority charge carriers and holes can be neglected, and yeah, okay. So what is the formula of conductivity? I know that this is an n-type of n-type semiconductor. In n-type semiconductor, electrons and holes will be drifting in the opposite direction. So because of them, the current will be in the same direction. So effective conductivity I can write down nq mu n plus pq mu p. Now you know that what is the formula of n? Sir, the formula of n is nd by 2 plus under root nd by 2 whole square plus ni square. Now in this question, ni value is given? No. So by default, if ni value is not given, you will assume that ni is pretty low. Ni is very lower than nd. If ni value is not mentioned, by default you will take that doping concentration is very high. So n will be approximately equals to nd only. And second line they have given that holes can be neglected. Or how you would have find the holes? Ni square by nd. But again you are not having ni value, so you will have to ignore the minority carrier concentration. So if ni value is not mentioned, then you will only consider the majority charge carriers. You will not consider this particular value. This particular value you will put to 0. Basically you will say that, sir, minority charge carrier concentration will be 0. Holes will be 0. I will only consider the electrons. Now how many electrons would be there, sir? So the number of electrons will always be equals to the dopant concentration, considering 100% ionization. Here it would be written full dopant ionization. So what they have considered? They have considered full dopant ionization. That means all that 10 to the power 16 atom, all that 10 to the power 16 atoms is giving you one free electron. So forget about the intrinsic carrier concentration, forget about everything. Whatever that donor atom that you are putting, all those donor atoms are giving you free electrons. That's it. This is what you will assume. So this 10 to the power 16 free electrons you are having. So your n is equals to nd here. So what will be the answer? Answer will be nd q mu n. What is the value of nd? 10 to the power 16. Everything is going into centimeter. What is the value of q? 1.6 into 10 to the power minus 19. And what is the value of mu n? Value of mu n, from here I can see that it is 1200. Okay, so what you can see is there here 10 to the power 3, 10 to the power 19, 1.6 into 1.2. That answer you are getting. 1.6 into 1.2. So 1.92. So from here conductivity you are getting 1.92 Siemens per centimeter, because everything is there in the centimeter. Just I am putting the value. What is the value of nd? 10 to the power 16. What is the value of q? 1.6 into 10 to the power minus 19. What is the value of mu n? 1200. So what you are getting? 1.6 into 1.2. that would be 1.92. So this would be the answer. Do we have more questions? No. Let's see the IV characteristics. So this is any random type of semiconductor. It could be intrinsic, it could be N-type, it could be P-type. So any random type of semiconductor is there. Across this semiconductor, you have put a battery of V, and now you are measuring this current. So with respect to this voltage V, how this current will go? Any kind of device that you make, whenever you go into the industry, wherever you go, any kind of device that you are having, your first target will always be to measure this IV characteristics. That if I increase my supply, this is the supply, that means this is your power. If I increase my power, how my current will increase? This is not about semiconductor. Even if you make diode, you make BJTs, you make MOSFET, or you make FinFETs, you make any kind of devices in your industry, wherever you go, I create something out of the box. My first target will always be IV characteristics. That with respect to the voltage, how much current I am getting. So let's try to find out the answer here. So what do you know? What is J? J is equal to sigma I. So we are considering any random semiconductor, not N-type, P-type, nothing. For any particular random semiconductor, J is equal to sigma I. What is your I? I will be J into A. So that would be sigma E into A. What is the formula of sigma? N Q mu E. What is N here? Number of electrons? No. N is charge carrier. It could be anything. N is simply charge carrier, right? Here what is the N? N is charge carrier. It is not free electron. It could be anything. Any charge carrier it is. Okay. So this is your I. Now what do you see? I is equal to NQ. Can I put this as VD? Yes. So number of charge carriers for a particular semiconductor, that would be constant, right? If it is intrinsic, then N will be equal to Ni. If it is N-type, then N will be equal to approximately equal to Nd. And if it is P-type, then N will be approximately equal to Na, right? So there my majority will be holes. In N-type, majority will be electrons, and in intrinsic, holes and electrons will be constant. Both will be same, right? So this will be a constant value. Q is already a constant, and cross-section area will also be constant. Basically, you are not changing the semiconductor, no? So for the semiconductor, cross-section area will also be constant. So you can directly see that I is proportional to VD. So this is the first relation that I am getting. I is proportional to VD. Now what is the next thing? What is V? V is equals to E by L. Let's just say the length of this particular semiconductor is L. So V is equals to E by L. So can you say that your V is proportional to ED? Sorry, V is proportional to E. This is the second equation we are having. Have we drawn the graph of VD versus E? Have you drawn the graph of VD versus E? Yes. So similar kind of graph you will get for I versus V. That's why I said that this graph is very, very important. Because I know the graph of VD versus E. If I know the graph of VD versus E, I can directly comment on the graph of I versus V. So VD is proportional to I, E is proportional to V. Or you can just think that if V increases, then E increases. If E increases, VD increases. If VD increases, I will increase. So there you go. If V increases, E increases, E increases, VD increases, VD increases, I increases. So there you go. It will increase. But after some time, what will happen is that if V increases, E will increase, but VD will increase, but slowly. So if VD is increasing slowly, then I will also increase slowly, or you can call it sublinearly. And after some time, what will happen is that if V increases further, then E increases further, then VD doesn't increase further, it will become constant. So I will also become constant. So this is the graph we will get. Now what I will do is that I will make two more graphs. I will make two more graphs, and then I will ask you a question. Let me make the graph and then wait for my question. I hope that some students would have already understood what the question would be. What do you think? What will be the question? I will be asking you that three graphs I have made. Which of the graph is for intrinsic semiconductor? Which of the graph is for extrinsic semiconductor? Which of the graph is for N-type, and which of the graph is for P-type? So three graphs I have made, I versus V graphs I have made. Which of them is for intrinsic? Which of them is for P-type, and which of them is for N-type? So who is having the maximum current at a certain voltage? Let's just say this voltage was 2 volt. So at a fixed voltage, who is having the maximum current? So maximum current this particular graph is having. And who will have the maximum current? N-type semiconductor will have the maximum current. Why is that so? Because mu n is greater than mu p. So this would be your N-type. And between extrinsic and intrinsic, which semiconductor will have more current? Extrinsic semiconductor will have more current, or intrinsic semiconductor will have more current? Extrinsic will have more current. So this has to be P-type. And this has to be intrinsic. There you go. This IV characteristic graph also we have made. All good? All fine? Okay. Again, a very important graph. Very, very important graph. Yeah. So this particular graph things are completed now. Okay. So on graphs only we have spent, I guess, 2 hours. So all the graphs we have seen in 2 hours. So graphs and some numerical problem also we have seen. So in the examination, what may happen is that directly they can make some graph and they can ask you which of them will represent the correct graph, or they can ask some questions as well. Okay. So I hope you have understood these particular analysis in a very good manner. Next, we need to study about diffusion current. Before that, we need to build up the base. So here we will be building up the base, but we are going to understand about diffusion current now. So till this point, what we were doing? This was your intrinsic semiconductor. In this intrinsic semiconductor, let's just say I am doping donor concentration. So if I am doping donor concentration, then how I was doping it? How I was showing it? That's a positive sign, positive ion giving you an electron, 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 positive ion giving electron, positive ion giving electron. So your electron concentration, if I say this is your x equals to 0 and this is your x equals to L. So whatever the electron concentration I get at x equals to L by 2, the same concentration I am getting at x equals to 0, the same concentration I am getting at x equals to L by 4, the same concentration I am getting at x equals to 3L by 4. So your electron concentration with respect to x was constant. It was always constant. And now what I used to do is that I used to apply some electric field, then your electron would have moved opposite to the electric field and the current would flow. This was the scenario I was doing. But now what I am doing is that I am doing non-uniform doping. So this was known as uniform doping. So now what I am doing is that here I am doping more. What I am saying, here donor atom is more. Here donor atoms are more. But at this side donor atoms are less. Are you able to understand this point? Here donor atoms are more, but here donor atoms are less. So now if I plot the graph of doping concentration versus x, then it will not be straight line. Just in a rough manner I am making the graph. Like let's just say here doping concentration is, here the donor atoms are more. Basically here the number of electrons are more, but with the distance it is decreasing. It can decrease linearly or it can decrease exponentially, or in whatever the manner it is decreasing, it is actually decreasing. So at x equals to 0, whatever the number of electrons you are getting, at x equals to L, the number of electrons are not same. At x equals to L by 2 as well, the number of electrons are not same. So they can decrease linearly or they can decrease exponentially. Whatever the graph is there, I don't care. But I just know one thing, that there is some gradient. What is the meaning of gradient? Gradient means that at this particular distance, at this particular point, the number of concentration is more, and at this particular point, the concentration is less. So here the number of electrons are more, here the number of electrons are less. Now I am having a spray. If I press this button, what will happen? So you can see that these, you cannot see actually, but what you already know that the particle of these spray, whatever the particle that is getting out of this spray, what will happen is that they will move in the whole room. Those particles will move in the whole room. So wherever there is high concentration, it will always move from the low concentration. Let's just say there is this tank. There is this tank which is completely filled. This tank is completely filled with water. Now what I did, I put another tank here, and here I did some hole. Okay, what I did, I made some hole. The tank was already filled with water. So here there was more concentration of water, here there was no concentration of water. So what will happen? The water will flow from here to here. So always it is the nature of the particle that it will always go from higher concentration to the lower concentration. Only the moving particle. Out of these two guys, positive charge and electron, who can move? This positive charge can move? No. I told you this is not important for your current to flow. Who are responsible for the current to flow? Electrons and holes. So who can move? Electron and holes can move. So this positive charge cannot move. Who can move? Electrons can move. And you can see that here there is more concentration of the electron. Here there is more concentration of the electron, but here there is less concentration of the electron. So what will happen is that electrons will move from here to here. So what I can see, I will see that this particular electron is moving from x equals to 0 to x equals to L. From x equals to 0 to x equals to L. Now if the electron is moving in this direction, because of the movement of electron, what will happen? Some current will flow. Some current will flow. Now for the movement of this electron, did you apply any electric field? No, I did not apply any electric field. Here in this particular scenario, did I apply any electric field? No. So this electron is not moving because of the electric field. So you cannot call it drift current. What you will call it? Diffusion current. So what you will say that electrons are diffusing from x equals to 0 to x equals to L. So what you will call it? Diffusion current. Now you will say that, sir, without even applying the battery, I am getting some current. What you are thinking that, sir, without even applying the battery, I am getting some current. Is it ever possible? This material, I don't apply any battery. Will it give me some current? No. So it is not possible. That means you are missing out on something. So what you are missing out? You are missing out that if these electrons are moving here, then they are leaving behind a positive charge. What really happened is that at x equals to 0, the positive charge has been accumulated, and at x equals to L, although the electrons will move and they will make sure that electron concentration becomes similar at everywhere, but what will happen is that at x equals to 0, there has been an accumulation of the positive charge, and here there are electrons. At this side there is an electron, and here there are positive charge, and this is positive charge is positively charged and electrons are negatively charged, and because of positive charge and negative charge, what will happen is that there one electric field will be built up, and this electric field is known as built-in electric field. What this electric field is known as? Built-in electric field. Again, let me explain it. The doping was non-uniform. Here there was more concentration of electrons, here there was less concentration of electron. Electron will move from higher concentration to the lower concentration, higher concentration to lower concentration. Since electrons are moving, there will be a current flow in the opposite direction of the electron flow. So electrons are moving from x equals to 0 to L, so current will flow from x equals to L to x equals to 0. This current is known as diffusion current because it is not flowing because of the electric field. It is flowing because of the concentration gradient, or you can say that electrons are diffusing, that's why this current is flowing. If the electron diffuses, what really happens is that at x equals to 0, there is positive charge that is being accumulated, and at x equals to L, you are having some electrons, some negative charge you are having. So positive charge and negative charge, because of that there will be one electric field from the positive charge towards the negative side. So this is the built-in electric field. Now in this built-in electric field, in this particular built-in electric field, this built-in electric field has been built up. In this particular built-in electric field, who are there? Electrons are there. There are electrons available. So because of this built-in electric field, electrons will move in which direction? Because of this built-in electric field, electrons will move opposite direction to the electric field. This is the direction of the electric field. So where the electrons will move? Electrons will move opposite. So electrons will move opposite. Electrons will move opposite. Is it clear to you? First, electron started diffusing. Because of the diffusion, what really happened was there was some electric field build up. Because of this electric field, again the electrons will feel another force, and that force will be opposite to the direction. That force will be from x equals to L to x equals to 0. So again these electrons, this was also electron, this was also electron. So again these electrons are drifting. Here electrons are diffusing. But here I will use the word electrons are drifting. Why is that so? Because these electrons are moving because of this built-in electric field. And I told you, if there is an electric field, that means drift word will come into action. So here electrons are diffusing because of the potential gradient, and here electrons are drifting because of the built-in potential, or you can say built-in electric field. And if electrons are drifting in this direction, then there will be a current flow in the opposite direction of the drift. and that current flow will be in this direction, and this current will be known as J drift. So you can see that this is the direction of diffusion current, this is the direction of drift current, both will cancel out each other. There you go. Did you understand this point or not? Let me explain everything again. It is not tough. At one go, in the initial phase, it may feel like that, sir, it is tough, but slowly you will be able to grasp it. What we did, this was a semiconductor, it was non-uniformly doped. At one side, we were having more concentration, at the other side, we were having lesser concentration. So electrons started moving from more concentration towards the lesser concentration. Since they are moving, they are moving not because of the electric field, but they are moving because of the concentration gradient. Okay, because more concentration, less concentration. So electrons are diffusing from x equals to 0 to x equals to L. So this was your x equals to 0 and this was your x equals to L. So electrons are diffusing from x equals to 0 to L, and since they are diffusing from x equals to 0 to L, there will be a current flow in the opposite direction. That current is known as diffusion current. Here you felt like that, sir, I have created the current. But actually what really happening is that since the electrons are diffusing, there has been some positive charge build up here and there has been some electrons have been built up here. Because of the positive charge, negative charge, there is a built-in electric field that has been built up. This electric field we are not applying. This electric field has been built up in the semiconductor itself. So this electric field has been built up from x equals to 0 to x equals to L. Because of that, electrons will be drifting in the opposite direction of the built-in electric field. So electrons are drifting in the opposite direction, and since they are drifting in this direction, there will be a drift current flowing from x equals to 0 to L. So direction of diffusion and drift current are opposite to each other, so they will cancel out each other and the total current will be 0. Because it is pretty obvious that in a semiconductor, if you are not applying any external electric field, then how the current can flow? Current cannot flow, right? For the current to flow, external electric field is important. So if you haven't applied the external electric field, first you felt like that some current is flowing, but actually there has been some built-in electric field. Because of that, electrons are drifting in the opposite direction and the current is also flowing in the opposite direction. So they are cancelling out each other and the total current is 0. Now you know the expression of drift current, but you don't know the expression of diffusion current. So that expression I am going to write down. So the diffusion current density due to electrons is given by J diffusion. What I am writing? J and diffusion I should write down. J and diffusion. So that is given by, you have to remember the formula. Okay. So that is Q dn dnx by dx. Sir, what is this dn? I will tell you everything. But just let me know one thing. Here there is a concentration gradient. That means whatever the concentration you are having at x equals to 0, at x equals to L, you are having different concentration. So I am making any rough graph. The nature could be anything. The nature could be linear. It could be exponential as well. So we don't know what is the nature. Whatever the nature is there, we don't care about that. Basically, whatever the nature is there, we don't care about the nature. But I just know one thing, that the concentration is changing with respect to x. That thing I know. Okay. So there will be, here if I put, here if I ask you to find out the value of dnx by dx, what that would be? 0. So what will be the diffusion current? 0. So Q into dn into dnx by dx. What is this dn? This dn is known as diffusion constant or diffusivity. What it is known as? Diffusion constant. Diffusion constant or diffusivity. Diffusivity. What is this nx? You already know, right? Concentration of electron, nx, electron concentration at a particular point x. Concentration of electron with respect to x, or concentration of electron at a particular x, that is nx, and this is just the differentiation Q, already you know. Now sir, what is this dn? So dn, formula of dn would be mu n into Vt. This is the formula. D is equals to mu into Vt. The similar formula we will write down for the holes as well. So what will be that formula? dp is equals to mu p into Vt. How will you remember? Do you remember ABCD? Do you remember the alphabet? So D will come first, then U will come, and then V will come. So D is equals to UV. So dn is equals to mu n Vt. People actually, like, usually they will forget that, sir. Some will write down, sir, mu n is equals to dVt, and like usually they can forget the formula. So how do I remember? I remember the alphabets. So A, B, C, D, U, V. So dN is equals to mu n into Vt. So this formula you are going to remember. This expression, this relation was given by Einstein, but you don't need to remember the name of Einstein. This relation was given as Einstein, so this is known as Einstein relationship. But you don't need to write it down. You just need to remember dN is equals to mu n into Vt. Okay, all good. So will you be able to remember the formula of diffusion current density? So this is your diffusion current density, Q into dN into dnx by dx. Now when we write down this formula for the holes, when I write down this formula for the holes, here I have written down for electrons. So when I write it down for the holes, there will be, I will be putting one negative sign here. When I write it down for the holes, I will be putting one negative sign. Why I will be doing so, that I will explain later on. As of now, you just remember this is the formula. Okay. Now another thing you can notice, at equilibrium, equilibrium means no external electric field applied. At the equilibrium, that means under no external electric field. What is happening? Under no external electric field. Under no external electric field, let me again draw the diagram. What was happening here is that there was electrons were diffusing. Here there were more electrons, right? Here there were more electrons. Here there were lesser electrons. So electrons were diffusing in this direction. So there was a diffusion current in this direction. So there was diffusion current in this direction. And since there has been a lot of positive charge and there has been lesser positive charge, so there has been an electric field build up in this direction. So there has been an electric field build up in this direction, that was known as E built in. From now onwards, I will write it down as EB. So this is the built in electric field. Because of this built in electric field, electrons started drifting in the opposite direction, and because of that you get a diffusion current in this direction. So you are getting, drift current in this direction. So can I write it down in this manner that your J diffusion is equals to minus of J drift if there is no external electric field applied. So J diffusion is equals to minus of J drift. So what will be the expression of J diffusion? That would be Q into dN into dnx by dx. Look, how do I actually remember? What was the formula of a drift? NQ. What was the formula of drift current density? What that was? Sigma E NQ mu E. So look, Q same. In place of mu, what is coming? dN is coming. Just a way to remember. Q same. In place of mu n, who is coming? dN is coming. When it comes to diffusion current, there is no electric field. So forget about the electric field. Who is left? N is left. But here, what is happening? There is a concentration gradient. So that's why I will put dnx by dx. Just a way to remember I am telling. If I remember the formula of a drift current, which is sigma E NQ mu E. So Q same. In place of mu n, what is coming? dN. Electric field is not there. Now in place of n, what will come? dnx by dx will come. Because there is a concentration gradient. Just a way to remember I am telling, nothing else. What is drift? What will be the formula of drift current? What will be the formula of this drift current? So which particles are moving? Electrons are moving. What is the formula of drift current? That is sigma E. Sigma E is NQ mu E. In place of n, what I will put this time? Nx I will put. Why is that so? Because electron concentration is not same at all the places. It is varying with respect to n. So Nx I will put. Negative sign is already there. Q I will put. In place of mu I will put mu n and E. In place of E, what I will put? E built in I will put. Because electrons are moving because of this built in electric field. So is this relationship clear to you or not? All good? All fine? Right? So what will happen? Q and Q will get cancelled out. Now EB is equals to minus dN by mu n minus dN by mu n into 1 by nx dnx by dx. This is the formula of built-in electric field you are getting. Now what is this dN by mu n? What did I tell you? D is equals to UV. A, B, C, D, D is equals to UV. So mu n into Vt. From here you can see that dN by mu n is Vt only. So what is your built-in electric field? What is the formula of built-in electric field you are getting? That you are getting as minus Vt by Nx dNx by dx. When you are watching this lecture, you are not going to forget this formula, because again and again we will be solving a lot of question on this particular formula. But in longer run you might forget it. What I am saying, when you are watching this lecture you will not forget this formula, but in longer run you might forget it. So concept should be clear to you. Within seconds you will be able to derive it. So drift and diffusion will be equal and opposite to each other. So drift diffusion is equals to drift. Write down both of the formula. Within second you will be able to derive it. So minus Vt by Nx dNx by dx. That's it. Okay. Just another way I am telling. Just one another way of looking at it. What I am doing is that, so formula of built-in electric field you have got minus Vt by Nx dNx by dx. In longer run you might forget it, so what you will do is that you can derive it as well. So what you will see, can I write it down in this manner? What will be the value of this particular thing? 1 by Nx dNx by dx only. So 1 by Nx dNx by dx I am replacing by this particular value. What is the differentiation of ln fx? That would be 1 by fx into differentiation of fx. So 1 by nx differentiation of nx, right? So another formula for the built-in electric field I have written down here. And this built-in electric field could be a function of x as well. What I am saying is that it could be constant or it could be a function of x as well, because this is also a function of x. If you do the differentiation, who knows that it might be a function of x only. This is also a function of x. So built-in electric field could be a function of x. So this is the answer that you are getting. Now from here, if you want to find out the potential different, like this is your built-in electric field, this is the built-in electric field is built up. If there is electric field, that means there will be electric potential as well. So this built-in potential, what this is known as built-in potential. So if you want to find out the built-in potential, that built-in potential is given by, how did I write it down? I have already explained it, right? Because Ex is equals to, here I have already told that Ex is equals to minus dV by dx. So from here Vx would be equals to minus Ex dot dx. So don't mug up anything, we will solve the numericals, you will understand how to utilize these kind of formula in the questions. If you want to remember something, you can remember this one, that's it. Sir, how I will use it in the questions, don't worry about that. So as of now, we have started studying about our non-uniform doping, that means we have started studying about diffusion current. So we took a semiconductor, then we doped it with donor atoms. We are not applying any external bias. Diffusion current and drift current are opposite to each other, they are cancelling out each other and total current is 0. Then only thing I need to remember is this formula of the diffusion current. Diffusion current because of the electrons. What is that? Q into dN into dNx by dx. dN is that diffusion constant or diffusivity. Value of dN is given by mu n into Vt. And now what is Vt? I forgot to tell what is Vt. Vt is thermal voltage, right? Vt is thermal voltage. Voltage at room temperature. Voltage because of the temperature, right? Vt is thermal voltage, and that is given by Kt, right? This thermal voltage is given by Kt by Q. So value of Vt at room temperature, Vt at 300 Kelvin. What is the value? 0.0259 volts, right? So I forgot to tell what is this Vt. Vt is thermal voltage. Thermal voltage at room temperature is 0.0259 volt, right? So you don't need to remember the value of Kt. Nothing you need to remember. Only thing you need to remember is that Vt is proportional to T. Vt is proportional to temperature. Vt is proportional to temperature. From here you can see that Vt is proportional to temperature, and the value of Vt at room temperature is 0.0259 volts. All good? All fine? And then we saw that at equilibrium under no external bias, what will happen is that drift current and diffusion current are same and opposite to each other. Then what we can do is that J diffusion is equals to minus J drift. If I do that, I will get this particular expression, that is minus Vt by Nx d by dx Nx. This particular expression can be written as minus Vt d by dx ln Nx. Using this expression, it will be easy for me to find out the built-in potential. But as of now, only thing you need to remember is this formula. Using this formula, how will you find out the built-in electric field? How will you find out the built-in potential? Everything we will see, don't worry about that. All good? All fine? Similar analysis you can do for the holes as well. And similar analysis, like let's go back to this slide. Here I said that at x equals to 0 there was more concentration, and at x equals to L there was lesser concentration. Opposite can also happen. What I am saying is that it may happen that here there is more concentration and here there is less concentration. So in this scenario, what will happen? Electrons will diffuse here. If electrons are diffusing here, that means this will be the diffusion current, right? Electrons are diffusing here, this will be the diffusion current. Since electrons are diffusing here, there will be more positive charge, there will be less negative charge. So electric field will build up in this direction. So this will be your built-in electric field. Since this is the built-in electric field, the electrons will move in this direction. So electrons will be moving in this direction. That means you can say that electrons are drifting in this direction. So if electrons are drifting in this direction, then drift current will be opposite. There you go. Drift current will be opposite. So diffusion and drift are opposite to each other. So it's not necessary that, sir, at x equals to 0 there will be more concentration, at x equals to L there will be less. Opposite can also happen. At x equals to L there is more concentration, at x equals to 0 there is lesser concentration. So opposite thing can also happen. The similar kind of analysis you can see in the p-type semiconductor as well, where I have said that at x equals to 0 there is more concentration and at x equals to L there is lesser concentration, but let's do it opposite. Okay, just for the thrill, let's do the opposite, that at x equals to 0 you are having lesser concentration, but at x equals to L you are having more concentration. All good? All fine? So holes will diffuse from here to here. Holes will diffuse from x equals to L to 0. If holes are diffusing in this direction, the diffusion current will also be in the same direction. So this will be your diffusion. And since holes are diffusing here, what will happen is that there will be negative charge, and holes have diffused here. So here there will be holes. So this is negatively charged, holes are positively charged. So what will happen is that there will be a built-in electric field from holes to negative charge. So this will be the built-in electric field. This is the built-in electric field. Now where the holes will move? Holes will move in the same direction to the electric field. So this was holes are diffusing. Now because of this built-in electric field, holes will drift. Holes will drift in the same direction as the electric field. So holes are drifting. And what will be the direction of current? Direction of current will be in the same direction of the hole drift. So if holes are drifting, holes are drifting in this direction, so what will be the direction of drift current? This will be the direction of drift current. So you can see that diffusion current and drift current are opposite to each other and they will cancel out each other. I hope you have understood. Holes will diffuse. Since they are diffusing here, this will be the diffusion current. Because of that, electric field is built up. Holes are drifting in this direction. Drift current is also in the same direction. So diffusion and drift current are opposite to each other and they will cancel out each other, right? So what we have done is that at x equals to L there is more concentration and at x equals to 0 there is lesser concentration. So x equals to L to x equals to 0. Oh, sorry. At x equals to 0 there is lesser concentration, at x equals to L there is more concentration. So this is how I can make the graph. It can be exponential as well. I don't care. The nature could be exponential as well. Whatever the nature is, I don't care. It could be exponential, it could be linear. I just know one thing, that at x equals to 0 lesser concentration, at x equals to L there is more concentration. What will be the formula of diffusion current? So diffusion current for holes. Here I write down diffusion current for electrons, Jn. So I am writing diffusion current for holes, Jp. That is given by minus q dp dpx by dx, where your dp is mu p into Vt. Sir, why this negative sign here? Sir, here there was no negative sign. Why this negative sign? So let's understand. here the diffusion current is in the same direction as the diffusion. What I mean to say is that, what is the direction of diffusion current here? This is the direction of diffusion current. If I make the diffusion current is from x equals to L to x equals to 0, right? But if you are going from x equals to L to x equals to 0, your slope is negative or positive? If I go from x equals to 0 to x equals to L, then my slope is positive. But if I am coming from x equals to L to x equals to 0, then my slope is negative, no? Are you able to understand this point? So slope will be negative, dpx by dx will be negative. And if slope is negative, so my current Jp, that will also be negative. Basically, current can never be negative or positive. If 2 ampere current is flowing, 2 ampere current is flowing. So this negative sign is just showing the direction. It is showing that this negative sign is showing that in whatever the direction holes are diffusing, in the same direction diffusion current is there. So even if you forget the negative sign, no need to worry about that. What you can do, you can analyze the condition that, sir, here there are more holes, here there are less holes. So where the current will be flowing? From more holes to the less holes. So holes are diffusing in this direction, so this will be the direction of diffusion current. So this is just for the sake of direction. What I mean to say is that if I put the value of dp by dx here, what I will do? dp by dx, with the increasing x, my concentration is increasing. So this value will be positive. dp by dx will be positive. With the increasing x, my concentration is increasing. So here the slope is positive. So this value will be positive. Q dp. dp will be positive, Q will be positive. Now the total answer is becoming positive. What does that mean? So what people will think that in the direction where px is increasing, in the same direction current is flowing. But no, the diffusion current is flowing in the opposite direction. The diffusion current is flowing where px is decreasing. Px is decreasing from x equals to L to x equals to 0. Your whole concentration is decreasing from x equals to L to x equals to 0. And diffusion current is also flowing from x equals to L to x equals to 0. Again, let me repeat the statement. Your whole concentration is decreasing from x equals to L to x equals to 0, right? And your diffusion current is also flowing from x equals to L to x equals to 0. So your diffusion current is flowing in the decreasing direction of whole concentration. That's why there is a negative sign here. What is the direction of diffusion current? This is the direction of diffusion current, right? This is the direction of diffusion current. In this direction, your electron concentration is increasing, because here there were more concentration and here there were less concentration. What was the direction of diffusion current? This was the direction of diffusion current. So the direction of diffusion current is in the increasing direction of electron concentration. But in case of holes, what was happening? Let's just say there were more holes. Here there were more holes and here there were lesser holes. So what will happen? Holes will diffuse here, and since holes are diffusing in this direction, so diffusion current will be this as well. So in case of holes, what happens? The diffusion current is in the decreasing direction of the hole concentration. But in case of electrons, the diffusion current is in the increasing direction of the electron concentration. So that's why when I write down the equation for electrons, I don't use any negative sign, but when I write down the equation for holes, I use the negative sign. Even if you forget the negative sign, there is no use of that. They will ask the magnitude of current, okay? And if somewhere the sign is being used, you will be able to do the analysis. Don't worry about that. So don't worry about this sign, only you remember this particular thing, q dp by dx. Here as well, sir, do I need to remember this sign? Don't worry, don't remember this sign. We will solve the numerical and you will get to know that there is not much importance of this sign. Without even remembering this sign, you will be able to solve the problems. Here also you don't need to remember this negative sign. All good, all fine. So your drift current is q dpx by dx. Drift current density. It is your drift current density, where this is the formula of your dp. Can you find out at equilibrium what will happen? At equilibrium. Equilibrium means no external bias. So diffusion and drift current will be opposite and equal to each other. So J diffusion will be J drift. Okay. So what is the formula? This formula is minus q dp dpx by dx, and here minus charge carrier q mu p and built-in electric field, which could be a function of x. So q and q will get cancelled out. So eventually your EBX will come out to be the similar answer, just here negative sign and negative sign will get cancelled out. So answer would be Vt divided by Px dpx by dx. Sir, in this formula there is no negative sign, but sir here there was a negative sign. So sir, will I mug it up that in the electron, if I write down the formula of electron current, then there will not be any negative sign. When I write down the expression of built-in electric field, then there will be negative sign. But here there will be negative sign, here there will not be negative sign. Forget about the negative sign, positive sign. Always you will take positive sign. No numerical will be wrong, because we will be solving the numerical. We will be making the direction with respect to the concept, not with respect to these signs. So we will solve the question with the concept. We will draw this diagram. We will see that where there is more concentration, where there is less concentration. Based on that, we will be able to know what is the direction. So when we solve the numerical, we don't need to care about these negative positive sign. Just the formula should be clear. What is that formula? That what would be the formula of diffusion current? That would be Q into Nx dnx by dx, Q into dp dpx by dx. And what will be the formula of built-in electric field? Vt by px dpx by dx, Vt by nx dnx by dx. That's it. Just if you remember the formula, and even if you forget this formula, you will be able to derive it within seconds. So don't worry about the signs. Okay, positive sign, negative sign, you don't need to worry about that. All good, all fine. So now we are going to see the numericals. So this question we are going to solve, this question we will solve, this problem we will solve, and this problem, and then this question. So I have put 5 questions here. With 5 questions, everything will be revised, whatever that we have studied. Every single thing will be revised. So let me take a break. You try solving these problems. You try solving this one, then you try solving this one. This is a very good question. So here you need to take care of something. Temperature you see, 400 Kelvin. Okay. Try solving this one as well. You need to find out the built-in electric field, and you need to find out the potential difference as well. Then built-in electric field and the potential difference. And this is the best question, like best question ever that can be asked on this particular topic. And if you are able to solve it, for me you are under 100 any day, no matter whatever the rank you get in your GATE examination. But if you are able to solve it, for me you are any day GATE AIR under 100. Even if you get 1000 rank, for me you will always be under 100. For IITs it will be 1000 only. They will give you admission based on your 1000 rank only. But if you are able to solve it, that means you have understood everything. Okay. These questions are from Niemann only. This is from Niemann. This is also from Niemann directly. This is also from Niemann. These are also from Niemann, but I just changed some data so that I could make it more complex. This is also from Niemann only. This is directly from Niemann. Okay. But here I changed the data just so that I could make it more complex. Yeah. So you try solving it. I will take a break and then I will come back. And with that, this topic will also be completed. So yeah. Just let me take a break and then I will come back and we will start solving these questions. Yeah, hi everyone, welcome back. So did you try this question? In this question, what is given? The electron concentration is varying with respect to x. So a particular expression is given, Nx is equal to 10 to the power 15 e to the power minus x by ln, and value of ln is also given. So your electron concentration is varying with respect to x in this manner, that at x equals to 0, it is 10 to the power 15. And at x equals to infinity, what it will happen? E to the power minus infinity, that would be 0. So basically it is decreasing with respect to x. So in this manner it is going from 10 to the power 15 to it will decrease. Value of ln also they have given. What is, sir, what is this diffusion length? So when we study about low level injection, at that time I will take this particular thing into action. What is the meaning of diffusion length? As of now, you just understand that value of ln is 10 to the power minus 4 centimeter. That's it. Okay, so this is this kind of concentration gradient is there. What does that mean? That means, let's just say this is your semiconductor. This is your x equals to 0. What is this? X equals to something that you don't know. You don't know the length of your semiconductor, but you know that at x equals to 0, you are having the maximum concentration. That means here you are having the maximum concentration of electrons. But with respect to the distance, it is keep on decreasing, and when you reach at x equals to infinity, the electron concentration will be 0 only. But the length will not be surely infinity, it would be some centimeter or whatever it is. right? So diffusion coefficient is also given, the value of dn is also given, that is given as 25 centimeter square upon second. How can you write down the unit of dn? You know that d is equals to mu into vt, right? What is the unit of mu? Centimeter square volt into second. What is the unit of vt? Volt. So volt will get cancelled out, centimeter square upon second. This will be the unit. Okay. Charge also, you know, you just need to find the diffusion current density. So diffusion current density, because of the concentration gradient it is coming. Now you will say that the total current would be 0. Yeah, total current would be 0. But one component will be of diffusion, one current component will be of drift. And drift current is coming because of the built-in potential. They are just asking you the diffusion current. They are just asking you the diffusion current density. Only the diffusion component you need to tell. I know that total current would be 0, but here you will not say that sir total current will be 0. You will say that sir one component is diffusion, one component is drift. They are asking us the diffusion component. So diffusion current will be coming because of the concentration gradient. So your diffusion current would be, this is your diffusion current. So Jn of x I am writing down because it could be a function of x as well. Why it could be a function of x? Because what was the formula? Q into dnx by dx. So if you solve this particular value, this could be a function of x as well. So that's why I am writing down Jnx. It could be a function of x. So what is the value of q? 1.6 into 10 to the power minus 19. What is the value of dn? 25. Everything is going in centimeter square. And dnx by dx, can you differentiate it? What is your nx? Nx is given as 10 to the power 15 e to the power minus x by ln. So if I differentiate it, what I will be getting? Sir, you will be getting 10 to the power 15 e to the power minus x by ln, 1 by ln and another negative sign as well. So your answer would be 10 to the power 15 upon ln e to the power minus x by ln. What is the value of ln? Value of ln is 10 to the power minus 4. So here I will put 10 to the power minus 4, here also I will put 10 to the power minus 4. Sir, negative sign will also come, but I will not care about the negative sign. Surely the negative sign will come, but you know that they will just be asking the current density. Answer will never be negative. If I say the current is minus 2 ampere, what does that mean? That means current, let's just say this direction I am taking as positive, and now I say that current is minus 2 ampere, that means current is flowing in this direction, that's it. So minus sign and anything, you don't need to care about that. So you let me know in which direction diffusion current will be flowing. So electrons will be diffusing in this direction, so the direction of diffusion current will be opposite to that. So this will be your diffusion current density. So if they ask you what is the direction of diffusion current, so it will be from right to left, that's it. Okay, so this is the expression of Jnx you are getting. Let's add up another page as well. So I will have to add the pages anyway. So Jnx I am getting as, so this would be 10 to the power 19 only, this will get cancelled out, 25 into 1.6, 25 into 1.6, 25 into 1.6, so that would be 40, right? 40, and this will be 10 to the power 19, this would be cancelled out. So 40 e to the power minus x by 10 to the power minus 4, everything is going in the centimeter, and what will be the unit here? Ampere per centimeter square. Okay, so this is the answer. Minus sign also you can take into action because everything is SI, only the length is in centimeter, rest everything is okay. Now you need to find at x equals to 0, x equals to 10 to the power minus 4 and at x equals to infinity. So first one is at x equals to 0. So your value of current density at x equals to 0. If you put x equals to 0 here, minus 40 ampere per centimeter square. Next, if you put x equals to 40, not 40, sorry, 10 to the power minus 4 centimeter, right? X equals to 10 to the power minus 4 centimeter. So you can see that this is also in the unit of 10 to the power minus 4. So this will also be in the unit of, sorry, this is in the unit of centimeter. So this x will also be in the unit of centimeter, and this would have been mentioned in the question as well, that x is in the centimeter. They did not write it down. It should be given in the question that x is in the centimeter, because ln is in the centimeter, no? So this x will also be in the centimeter only. So your Jn at 10 to the power minus 4 centimeter, that would be minus 40 e to the power 10 to the power minus 4 divided by 10 to the power minus 4. This is also in centimeter, this is also in centimeter. So your answer is coming out to be minus 40 by E. So you can solve it, minus 40 by E, you can do it and you will get your answer. (14.71). What this negative sign is representing? Negative sign is representing that the current is flowing in this direction. So where the holes are diffusing, where the electrons are diffusing, in the opposite direction the current is flowing. That's why the negative sign is coming in the final answer. And at x equals to infinity, what will be the scenario? At x equals to infinity, Jn of infinity. So minus 40 e to the power minus infinity. What will be the answer? E to the power minus infinity will be 0 only. So current will be 0 ampere per centimeter square. Very easy question, very straightforward. Just you need to apply the formula and you will get the answer. Nothing was there, only formula based. Free marks, I would say, free marks. If you just remember the formula q into dn dnx by dx, your job would be done. And forget about the negative sign, don't care about the negative sign. Let's go to the next one. A non-uniform doped p-type semiconductor is maintained at 400 Kelvin. So your semiconductor, p-type semiconductor is working at 400 Kelvin. The hole concentration is decreasing linearly from x equals to 0 to x equals to 0.1 centimeter. What does that mean? They have given the graph of hole concentration. Your hole concentration is decreasing linearly from x equals to 0 to x equals to 1. This is how it would be. X equals to 0 to x equals to 0.1 centimeter. This is how it would be decreasing. At 400 Kelvin, the diffusion current density is measured to be 20 ampere per centimeter square. The diffusion current density at 400 Kelvin. This is constant. It is not a function of x. I told you it could be a function of x. It could not be a function of x as well. And just tell me one thing. What would be the formula of diffusion current density? Just tell me what would be the formula of diffusion current density. That would be q dp dpx by dx. Right? This would have been the formula. And another negative sign also you can add. Even if you forget the negative sign, don't care about that. Now you just let me know the slope of this graph, what it will represent. The slope of this graph, what it will represent. Dpx by dx only. And will that be constant? Yes, the slope of this graph will be a constant value. Are you able to understand this point? The slope of this graph is constant, but slope of this graph would be different. This is simply y equals to mx plus c. So what will be the slope here? Slope will be some constant value m. So slope will be constant. For this graph, the slope will be constant. So if this slope is constant, this dp is constant, and q is also constant, that means this current density has to be constant. So yes, current density is constant, that is given 20 ampere per centimeter square. So just remember that everything is going in the centimeter. Now what they are actually asking, if the hole concentration is given at x equals to 0, they have given the hole concentration. What is the hole concentration at x equals to 0? They have given the hole concentration at x equals to 0 as 3 into 10 to the power 18 centimeter cube. You need to find the hole concentration at x equals to 0.05 centimeter. This is what you need to find. I know the Jp value, I know the Q value, I can find out the Dp value as well. How can I find out the Dp value? Because I have the mobility value. So what is the relation between Dp and mobility? That is mu p into Vt. But now here something interesting will come out. You need to find out the value of Dp. You need to find out the value of Dp, which is equals to mu p into Vt. So if I put the value of Dp, if I put the value of Q, if I put this value, then what I would be able to find out? Dpx by dx. And if I am able to find out Dpx by dx, then I can find out the hole concentration as well. So my major concern would be to find out the value of dpx by dx. For that I would require the value of dp. So value of dp, diffusion constant, that would be mu p into Vt. But it is working at 400 Kelvin. So you need to find out the value of dp at 400 Kelvin only. And you are given mu p value at room's temperature. What it is given? Mu p at 300 Kelvin is given. What is that? 550 centimeter square volt into second. So how will you find out the mu p value at 400 Kelvin? Because everything you require at 400 Kelvin. So you require mu p value at 400 Kelvin, you require Vt value at 400 Kelvin. So now you know that after room's temperature, what you know, what is my target? My target is to find this particular thing, and you know that after room's temperature, mu p is inverse, mu p is proportional to T to the power minus 3 by 2. So mu p at 400 Kelvin divided by mu p at 300 Kelvin would be equals to what? Temperature 400 Kelvin to the power minus 3 by 2 divided by temperature 300 Kelvin to the power minus 3 by 2. So what you are getting? Mu p at 400 Kelvin, mu p at your 400 Kelvin is coming out to be 3 by 4 to the power 3 by 2, right? 0 will get cancelled out, and this will go upward, this will come downward, to the power 3 by 2 into 550. So this would be the answer. Basically it should decrease, that I already know. So 3 by 4 to the power 1.5, right? Into 550. So 357.23. So this was the best thing of this question. Actually in Niemann here 300 Kelvin was given, but just to make the question a bit complex, I changed it to 300 Kelvin. So what you are getting? This much you are getting. So this is the value of your mobility. And what about the Vt value? Sir, for Vt value I would require the Boltzmann constant. No, you know that Vt is equals to Kt. From here what you can see is that Vt is proportional to temperature. What does that mean? Vt at 400 Kelvin divided by Vt at 300 Kelvin will be equals to Vt at 400 Kelvin, you don't know, right? Basically Vt at 400 Kelvin you don't know, but Vt at 300 Kelvin you already know. Since it is proportional to temperature, so it would be 400 divided by 300. Say yes or no? Are you able to understand this point? So Vt at 400 Kelvin will be equals to 4 by 3 times of whatever Vt at 300 Kelvin. What is that? 0.0259 volt. Are you able to understand this point? So 0.0259 into 4 by 3. So 0.0345. 0.0345 volt. So this is your Vt value at 400 Kelvin. Now what I need to find? I need to find the dP value at 400 Kelvin. That would be mu p value at 400 Kelvin multiply with Vt value at 400 Kelvin. So mu p value at 400 Kelvin, what that was coming out to be 357.23 into 0.0345. And what will be the unit? Unit will be centimeter square upon second. 0.0345, whatever it is written, into 357.23. So this answer is coming out to be 12.33 centimeter square into second. So this is your dP value now. So this was the best part of this question. So dP value we have find out now. Now I can solve the question, right? So here also let's solve it. 1.6 into 10 to the power minus 19. Let's take it negative, because this negative sign I have put here. Okay, but negative sign, even if you forget, don't care about that. Now what is the dP value? Let's just say I have forget the negative sign. Forget about the negative sign. I told you negative, positive, just forget about everything. Just put down the values. What is the dP value I am getting? 12.33. 12.33 dpx by dx. Okay, so 12.33 into 1.6 into 1.6, then you take the reciprocal and then multiply with 20. So 1.01 into 10 to the power minus 19. So your dpx by dx, you are getting 1.01 into 10 to the power 19, or you can write down 10.13, 10 to the power 18. I will write it down in 10 to the power 18. So after doing the calculation, I am getting 10.13. 10.13 into 10 to the power 18. Okay. Now you know that the slope is negative only, no? From the graph only you could see that slope is negative. Basically, whatever the value at 0 you are getting, the value at 0.05 would be lesser than that. Because it is saying that it is decreasing linearly from 0 to 0.1 centimeter. That means at 0.05, the value will be lesser. So you already know that slope will be negative. So even if you had forget this negative sign here, directly you can put the sign negative here. Now from here, can you find out the value of px? Just take this dx at this point and then just px would be, just integrate. What I mean to say is that dpx would be minus 10.13 into 10 to the power 8 dx, and you will integrate. How you will integrate? You can integrate from 0 to a particular x, right? And here also you can integrate from 0 to a particular x. On both of the side I am integrating. So what I will get, here I am writing down. So that would be equivalent to px minus p of 0 to a particular x I am integrating. And here what you will get, minus 10 to the power minus 10.13 into 10 to the power 8 x, right? So value of px is coming out to be p of 0 minus 10.13 into 10 to the power 8 or 18 10 to the power 18 into x. And you can see that if I put x equals to 0, I am getting p of 0 only. So p of 0 value I already know. Now this is the final answer that I am getting. This is the final expression that I am getting. Now what I need to find? I need to find the value at 0.05 centimeter. 0.05 centimeter. So p of 0, concentration, where is the p of 0 value? 3 into 10 to the power minus 18, everything is going into centimeter only. So don't worry about the unit. 3 into 10 to the power 18 minus 10.13 into 10 to the power 18 into 0.05. I will not convert it into the meter. Why I will not convert it into the meter? Because everything is going into centimeter. So that's it. This would be the answer. So 10.13 it is, 10.13 it is, multiply with 0.05. Multiply with 0.05, that is 0.5, and that will be subtracted from 3. So what you are getting? 2.5, roughly around 2.5 into 10 to the power 18 per centimeter cube. So this will be the concentration. Is that clear to you or not? Very simple thing. Here also the expression for the value of current density was given. I know that I know the value of Q, I know the value of dP as well. From there I can find out how my whole concentration is decreasing. So if I know the expression of dP by dx, then from there directly I can find out the value of P of x just by integrating it. So here if my x is going from, here you should write down from P of 0 to P of x, because here you are putting the limit of Px, no? So from P of 0 to, if I am going P of x, that means I am going from x equals to 0 to x equals to x, right? So I can simply integrate, I will get this value. Till this point I was doing something else. Or you can simply know from here only the slope is minus 10.13 into 10 to the power 18. That means if you move for 1 centimeter, then this much will be reduced. So if you move for 0.05 centimeter, then how much will be reduced? This much will be reduced. So if I am an intelligent student, what I would do is that I know the slope, I know the meaning of slope. If I have studied signal system, then I would know that what is the meaning of slope. That if you work for 1 centimeter, because the unit are the units are there in the centimeter only. So if I move for 1 centimeter, then my whole concentration will be decreasing for 10.13 into 10 to the power 18. But I need to move for 0.05 centimeter. That means I will multiply with 0.05 centimeter. That means my whole concentration will be decreasing by 10.13 into 10 to the power 18 into 0.05. So what was the concentration at x equals to 0? This was the concentration at x equals to 0. And how much it will be reduced? This much it will be reduced. So your approximate answer would be 2.5 into 10 to the power 18. That's it. The best thing was here the temperature was 400 Kelvin. So if different temperature is given, people will be thinking that you need to remember the formula of you need to remember the Boltzmann constant, but you don't need to remember the Boltzmann constant. You just know that Vt is proportional to temperature and your mobility is proportional to 10 t to the power minus 3 by 2. So it will decrease and this will increase. So this value has decreased and this value has increased. All good? All fine? Okay then. Let's move to the next question. The electron concentration in the silicon is given by this thing. This is how the electron concentration is varying. X is measured in micrometer. So this they have given, X is measured in micrometer. So this 18 would also have been in micrometer only. The question is not written in the correct manner. This would also be in micrometer. So here they should have written minus X by LP, then they would have said that LP is 18 micrometer. Okay, so this would also be in micrometer. And your semiconductor is limited between 0 to 25 micrometer. What does that mean? What do you understand by this? I understand that this is my semiconductor which is going from X equals to 0 to X equals to 25 micrometer. Okay, this is the length of my semiconductor, and at X equals to 0 I am having the maximum concentration, and with the distance it is decreasing. With the distance it is decreasing. With the distance this concentration is decreasing. So what do you think? Here there would have been more concentration, and at this point there would have been lesser concentration. If I say this is my X equals to 0 and this is my X equals to 25, right? That means electrons will diffuse here. So on this side there will be positive, 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 and this side there will be negative. So what will be the direction of electric field? This will be the direction of electric field. This will be the direction of E field, right? This is your X equals to 0 and this is your X equals to 25. So your direction of electric field is from X equals to 0 to X equals to 25 micrometer. Okay. Diffusion constant, mobility, all these things are given. Temperature is not mentioned. Temperature is mentioned 300 Kelvin only. Everything is fine. The total electron current density is given as minus 40 ampere per centimeter square. The electron has both diffusion and drift current component. Determine the electric field as a function of X which must exist inside the semiconductor. So inside the semiconductor, which electric field will exist? That would be built-in electric field. So what they are asking? Built-in electric field. So even if you forget the formula, then you can derive it. I told you the diffusion current and the drift current will be opposite to each other and they will be cancelling out each other. So what would be the scenario here? What is the diffusion current? Sir, Q into dnx by dx minus nx q mu n and built-in electric field, right? Q and Q will get cancelled out. What you are getting? Built-in electric field you are getting as dn by mu n into 1 by nx dnx by dx. This is your built-in electric field that you are getting. Sir, negative sign, forget about the negative sign. Don't worry about the negative sign. Okay. What is dn? dn is 25. What is mu n? 960. Everything is going in centimeter square. So dn is 25, mu n is 960. 1 by nx. What is the value of nx? Value of nx is 10 to the power 16 e to the power minus x by 18. 10 to the power 16 e to the power minus x by 18. Right? This is in micrometer. This is also in micrometer. Can you differentiate the nx? Can you differentiate the nx? Yes, surely I can differentiate. This is your nx. 10 to the power 16 e to the power minus x by 18. So if I differentiate it, what you will be getting? 10 to the power 16 divided by 18 e to the power minus x by 18. So 10 to the power 16 e to the power minus x by 18 divided by 18. So negative sign will also come. Forget about the negative sign, I am telling you. Okay, here also negative sign would have come. Here also negative, so that would have been positive. Right? So negative sign, positive sign, we don't care. We just need to find out the value of built-in electric field. We also know the direction as well. So what we can see here is that this part and this part is getting cancelled. So what you are getting 25 divided by 960, but this 18 is in micrometer, right? But everything was going in centimeter. Here centimeter, centimeter, dn value centimeter, 960 centimeter, and jn is not useful for us, although it is given, but it is not useful. So what did you get to know? That this is in the micrometer, but I need to convert it into the centimeter. So what I will do, 18 into 10 to the power minus 4. This was the important part, because everything is going to centimeter, so I will take this also into centimeter only. Although here also I should have taken centimeter, but this is getting cancelled. But here it is coming in micrometer. 18 is coming into the micrometer, so 10 to the power minus 4. Then it will be into the centimeter. So now it will be okay for me. So what I would do is that 25 divided by 960 divided by 18 multiply with 10 to the power 4. So 14.46. 14.46 volt per centimeter. So this is your built-in electric field that I am getting. So what is the value of my built-in electric field? 14.46 volt per centimeter. It is coming out to be constant. It could be a function of x as well. Here I should have written it could be a function of x, right? It could be a function of x, but it is coming out to be constant. Right? Now what I need to find? I need to find the built-in potential. What is that? Dot dx. Right? Now what you need to find? Calculate the potential difference between x equals to 0 to x equals to 0 and 25 micrometer. That means from 0 to 25 micrometer you need to integrate. So what you will be getting? E built in, this is 14.46, that is constant. Forget about the negative sign. What you can see, from 0 to 25 micrometer, this is what they are saying. So what is the differentiation of a dx? That would be x only. From 0 to 25 micrometer, right? Micrometer. This is your micrometer. So what I would do, I will put 10 to the power minus 4, because this is in the centimeter, so this will also be in the centimeter only. So what will be the answer? 14.46 into, basically what was your V? Sorry, what was your electric field? Electric field was potential divided by the length. So what will be your potential? That will be electric field into the length. What is the length? Between 0 to 25 micrometer. So in the length I will put 25 micrometer. Or you can do in this manner, that E built in will come constant. You are integrating from 0 to 25 micrometer. Sir, you have forget the negative sign. Forget about it. Just hold on. Okay. We will get the answer. Just hold on. So 14.46, 25 into 10 to the power minus 4. So 14.46 into 25. So you are getting divided by 10 also I can do. So 13.16 millivolt. (14.46 into 25). 14.46 into 25. Yeah, and divided by 10 to the power 4. So 36.15 millivolt. Yeah. So this is the answer you are getting. Now sir, plus minus sign, how I will decide? So what they are saying, calculate the potential difference between x equals to 0 to potential difference between x equals to 0 and x equals to 25 micrometer. Let's just say this is 1 point. This is your VA potential, which is at 2 volt, and this is your VB potential, which is at 1 volt. If I ask you find the potential difference between VA and VB, what you need to find? VA minus VB. What would be your answer? 1 volt. Right? VA minus VB, 2 minus 1, 1 volt. If I ask you find out the potential difference between VB and VA, so you need to find out VB minus VA, that would be 1 minus 2 minus 1 volt. Here what you can see, x equals to 0 is at higher potential or x equals to 25 is at higher potential? X equals to 0 is at higher potential, no? Because at x equals to 0 you are getting positive charge. So that means this is the higher potential. Higher potential. So if I am finding the potential difference between x equals to 0 to x equals to 0 and x equals to 25, that means x equals to 0 is at higher potential. So final answer will be positive or negative? It will be positive only. So forget about this negative sign, here negative sign, wherever negative sign is coming. Don't care about those negative sign. If they are asking electric field, that means a negative sign will not come. But in the potential, in the answer, negative sign may be there. What I mean to say is that if they are asking electric field, then all the 4 options will be having different values. There is no meaning of a negative sign there. In the electric field, they can say that okay, the direction of electric field will be from x equals to 0 to x equals to 25. Or in one of the option, they will say that direction is there from x equals to 25 to x equals to 0. So you would know that the direction is from x equals to 0 to 25. So with this particular answer, they can give the direction. Direction is from x equals to, direction is positive x. What I am saying? Positive x. Positive x. What do you mean by positive x? That means you are working in the positive direction of x from 0 to 25. This is your 0. This is your 25. So if, and this is my x axis. So if I am working in this direction, this is my positive x, and if I am working in this direction, this is my negative x. Because from 25 to 0 if I am going negative x, from 0 to 25 if I am going positive x. So direction here is positive x. This is what they can say. Here plus minus sign could be there. The potential difference could be positive or negative. So how will you determine that, sir, x equals to 0 is at higher potential, x equals to 25 is at lower potential. And what they are asking, the difference between 0 and 25. So since this is at higher, this is at lower, so answer will be positive only. There you go. Okay. So this was the question. Here luckily our calculation was easy because this was not a function of x. But if it becomes a function of x, then finding the built-in potential by this formula will be a bit difficult. Are you able to understand this point? Which we are going to solve in the next question. But let's find out the value of built-in potential using a different formula. This is the answer, but let's use a different formula. In this problem only, what I am saying is that I am gonna find out the value of built-in potential using some different formula. So what is the formula of my E built-in? That is minus Vt by Nx. Forget about the negative sign. Just forget about the negative sign. dnx by dx. And I told you, you can do something like this. Okay, this is your built-in, and it could be a function of x as well. It could be a function of x. What I need to find? I need to find built-in potential, and that I know that it would be E built-in dot dx. Negative sign, anything, everything I am forgetting because I know that in the final answer I can change it. So what I will be getting? Vt. What is my E built-in? This is d by dx ln nx dot dx. Basically I am just putting this value, E built-in x. E built-in x I am putting dot dx. So you can see that dx and dx is getting cancelled out. Vt is a constant value. Vt can be outside. So basically d ln nx. What is the answer of d of ln x? And you are integrating it. What would be the answer? If you don't know by this, so what would be the answer of d of fx? If you are integrating it, what is the answer of d of x? If you are integrating from 0 to x. So answer would be 0 to, let's integrate it from 0 to alpha. So answer would be, sir, x integrating from 0 to alpha. So what would be the answer of d of fx? Basically this and this will get cancelled out. So answer would be fx, but you need to put the limit. You need to put the limit of fx. Are you able to understand this point? So similarly here as well, d of ln x. So this and this will get cancelled out. Answer will be ln x. But I need to put the limit. I need to put the limit of whatever that is inside. I need to put the limit of whatever that is inside. So now in our case, what is there? Ln of fx. Ln of fx. So this and this will get cancelled out. Ln of fx. But now I need to put the limit of fx. So from fx, f1 of x2, I am going to f2 of x. I am not putting the limit of x. I am putting the limit of fx. Are you able to understand this point? This and this was getting cancelled out. Here you are putting the limit of x. Let's just say it was d of sin x. So what you will say? Sir, this and this will get cancelled out. So answer will be sin x. And if I am doing the indefinite integration, then I need to put the limit. So you will put the limit of x. So in place of sin x, if I am putting fx, so I need to put the limit of x. Similarly, here my function is Here my function is ln, but inside ln there is another function. So I will put the limit of this fx. No, are you able to understand this point or not? Mathematics, again mathematics. Okay, mathematics only. D of ln x, this and sir, this will get cancelled, but since this will be a indeterminate this will be an indeterminate integration, so I need to put the limit of nx. So here this is how I am writing down the formula, that you will put the limit of nx. So this will be your final answer of built-in potential. So I need to find out the built-in potential. I need to find out the built-in potential from built-in potential between x equals to 0 to x equals to 25 micrometer, right? So what do you think, what should be my answer? V built-in, Vt, your answer was ln nx. This and this was getting cancelled, answer was ln nx. But now you are putting the limit. You are putting the limit. You are putting the limit from value of your electron concentration at x equals to 0 to the value of your electron concentration at x equals to 25 micrometer. So if I put this value, what I will be getting? Ln of nx at 25 micrometer minus ln of at 0 meter. Say yes or no. Did you understand this point? I am just putting this guy here. If the limit is given like this, fx going from x equals to 0 to x equals to 1, what would have been the answer? F of 1 minus f of 0, right? You agree to this point? Similarly, f of nx, and limit is also of nx only. So f of n of 25 minus f of n of 0. Is that clear to you? So what would be your final answer? Final answer will be Vt ln concentration at 25 divided by concentration at 0. So what is the value of Vt? From here Vt was actually dn by mu n, right? Dn by mu n ln concentration at 25, concentration at 25 micrometer, that would be 10 to the power 16 e to the power 25 by, that would be 10 to the power 16 e to the power minus 25 by 18, because this is also in micrometer, this is also in micrometer, so micrometer is getting cancelled. This will be a certain value divided by concentration at x equals to 0. So if you put x equals to 0, e to the power 0 will be 1, so divided by 10 to the power 16. So what you are getting, this and this will get cancelled out. Ln e to the power something, ln e to the power x, what is the answer? X only. So 25 by 18 you will be getting. Now sir, negative sign will come, but you know that answer should be positive. My built-in potential will be positive. Here I have explained it. So what will be the answer? dn by mu n, dn by mu n, this is your dn by mu n. So 25 by 960, dn by mu n, 25 by 960, 25 by 960. E to the power minus 25 by 18. Sorry, ln and e has been cancelled out, so 25 by 18. Answer will be positive only. I have forget this negative sign. At a lot of places, here also I forget the negative sign, right? At a lot of places I am forgetting the negative sign. So from here only the negative sign will come out, but I don't care about the negative sign. I even don't care about the limit, that sir n equals to, sir from here x equals to 0 to 25 you are going. You should have gone from 25 to 0. I don't care about all these things. I know that eventually they are going to be subtracted. The only difference I will get is that either my answer will be positive or negative, but I know that my answer has to be positive only. So if I solve it, I will get the same thing. 25 into 25. Sir, here you need to convert it into the micrometer, centimeter, anything? No. Why is that so? Because this was 25 micrometer, this was also micrometer. So micrometer got cancelled. So here no conversion is required. So 25 into 25 divided by 960 divided by 80. So 0.036, again the same answer I am getting, 36.169 millivolt. So eventually, what do you understand? Here I am writing down the formula of built-in potential. That is coming out to be Vt into, forget about the negative sign, Vt into ln some concentration divided by some concentration. Some concentration, it could be 25 micrometer or it could be 0. Whatever you want to put, you can put it. Divided by some other concentration. That's it. This would be the answer. Did you understand this point or not? Sir, N2 by N1, N1 by N2. Sir, what is N1? This is what is N2? N1 is the concentration at x equals to 0 or 25 micrometer. N2 is the concentration at x equals to 25 or at x equals to 0. Sir, whatever the answer you get, you know that answer would be positive only because they are asking the difference between x equals to 0 to 25. So don't care about what is N1, what is N2. You just know that I need to put the concentration at a particular point and at the other point. And then I just need to divide them and then take ln. You can see that this particular expression. Just keep your notice here. Keep your notice here. So what we have done is that from here we converted the formula in this manner. Then I know that if I differentiate, if I integrate, then dx and dx will come out and then I will integrate. So if I integrate, integration and d will get cancelled out, and what I would see is that limit of ln will go from one concentration to other concentration. So ln of one concentration to other concentration. So if I reach from this formula to this formula, there is only one thing involved, that is integration with respect to dx from one concentration to other concentration. The concentration at x equals to 0 or 25, the concentration at x equals to 25 or x equals to 0. I don't care about that because in the final answer only the sign will change, nothing else will change. I hope everything is making sense to you. Like when you study this particular topic, people will get confused in sign. Sir, positive sign would come, negative sign would come. I am telling that don't even remember the sign. Just remember the expression. ln, like in the PN junction as well, I will write down the same expression, and there also I will not tell that sir which value will come upward, which value will come downward. There also I will not tell. There also I will say the same thing, that you will solve the question there and just you will see the sign. You will draw the diagram in this manner. You will draw the diagram in this manner and then you will get to know that whether where the potential is positive, where the potential is negative. And in most of the times in the examination, they will ask only the magnitude of the potential difference. They will not ask the sign. They will ask only the magnitude. And if they are asking only the magnitude, then you would know how to solve it. So better than focusing on these formula and everything, we should focus on the diagram. If I am able to make the diagram, most of my job is done. Then I can write down the formula of built-in potential, then my job is done. Simply the answer would be Vt ln one concentration divided by other concentration. And you know that answer of built-in potential will be in volts. So here also I will be having volt only, and this would be some certain answer because concentration divided by other concentration. So unit to unit will be getting cancelled out. So this is unitless and this is having a unit of volt. So answer will be in volts. So this is how you can remember as well. Although in this question it was not required because it was not coming out to be a function of x. But if it was coming out to be a function of x, then this integration would have been a bit difficult for you. But even if it is coming out to be a function of x, what I have done is that we don't even require the built-in electric field. Without even calculating the built-in electric field, I can directly tell the answer of built-in potential. How will I tell? Vt ln one concentration divided by the other concentration. That's it. And how did I derive it? The complete derivation I have solved it. Dx get cancelled out, Vt d ln x, integration to d gets cancelled out, then one concentration divided by the other concentration. So if you keep your concentration, if you just listen to my words, then surely you will be able to understand it, right? So let's see this. Determine the induced electric field in a semiconductor in thermal equilibrium given the linear relation of the donor concentration. So sir, here they have given that donor concentration. Here they did not tell that sir it is the value of your number of electrons. What I mean to say is that someone will say, sir, number of electrons will be, sir, number of electrons nx will be equals to ndx by 2 plus under root. This doubt you may have, but what you can see that ni value is not given. So if ni value is not given, then you know that ni value is very small compared to this doping concentration. So you know that ni is not given, that means ndx is pretty larger than ni. Okay, so from here what you would see is that nx is approximately equals to ndx only, right? So this number of electrons, this electron concentration per unit volume is given. The length x is in the micrometer. Just make sure that I will use the length in the centimeter whenever it is required. So this is given. What you need to find? You need to find the potential difference. Okay, you need to find the potential difference. You don't need to find the built-in. Okay, electric field also you need to find. Induced electric field, built-in electric field they can call it, or induced electric field they can call it. So you need to find the induced electric field in the semiconductor in thermal equilibrium. Thermal equilibrium means there is a constant temperature. At that particular temperature there is no recombination, there is no generation. This process I have already told. I have told the meaning of thermal equilibrium. Also there is no battery also applied. No battery is also applied. So in this thermal equilibrium you know that there will be some built-in electric field. That electric field you need to find. Also you need to find the potential difference as well. So let's do it. And here also you know one thing. If I draw the diagram, so you can see that if x increases, then this donor concentration is decreasing. So if this is your x equals to 0 and this is your x equals to 1 micrometer, then with the increase in x, donor concentration is decreasing. That means the number of electrons will also decrease. So here more number of electrons are there, and here less number of electrons are there, right? So what will happen is that electrons will diffuse. Electrons will diffuse. So here they will create the positive charge and here they will create the negative charge. So the direction of electric field will be again from x equals to 0 to x equals to 1. Okay, and what about the potential? This will be positive potential, this will be negative potential. So basically the answer again here will be positive only, because x equals to 0 is at higher potential and x equals to 1 is at lower potential, right? So let's find out the built-in electric field. So you can either derive the formula or you can simply write down the formula, that is Vt by Nx d by dx Nx, right? Negative sign is there, but I don't care about the negative sign. What is the value of, let's put the negative sign. What is the value of Vt at room temperature? It is going, so 0.0259 divided by Nx. Nx is 10 to the power 16 minus 10 to the power 19 into x, into the differentiation of this one, what that would be, minus 10 to the power 19, right? So what you are getting, zero point zero two five nine 10 to the power 19 divided by 10 to the power 16 upon 10 to the power 16 minus 10 to the power 19x. So this is coming out to be a function of x, right? So they can ask you what is the value of a built-in electric field at x equals to 0. So what will be your answer? So this and this will get cancelled out and 10 to the power 3 will be multiplied. So 25.9 volt per centimeters, because everything is going into the centimeter. Here you are not putting the value of x. Whenever you put the value of x, at that time you should be taking care, right? So if someone asks you what is the value of a built-in electric field at x equals to 0. So if I put x equals to 0, what I will do, 0.0259 into 10 to the power 19 divided by 10 to the power 16. So this will be gone, 10 to the power 16, 10 to the power 3. So what you are getting, 25.9. Answer will be in volt per centimeter. Now if I ask you what will be the value of a built-in electric field at x equals to 1 micrometer, what do you think, what will be your answer? I want your answer. I want to see what value you put here. So 0.0259 10 to the power 19 10 to the power 16 10 to the power 19. Here I need to put the value of x. What I will put? I know that everything is going into the centimeter. This is centimeter cube inverse, right? So only here only I need to use the value of centimeter cube. So here I am using centimeter cube only. So everything is going in centimeter. Now I need to put the value of x equals to 1 micrometer. So what I will do? X equals to 1 micrometer is equals to 10 to the power minus 4 centimeter. So in place of x, what I will put? 10 to the power minus 4. Are you able to understand this point or not? Okay. So 10 to the power minus 4, it would become 10 to the power 15. So it doesn't make much sense, right? 10 to the power 15, because 10 to the power 16 is larger than 10 to the power 15. If I want to make it 10 to the power, then 10 micrometer I would have to do. 10 micrometer is not even possible. So yeah, let's keep this only 10 to the power minus 4. So what we are getting 10 to the power minus 4. I was just thinking to change the problem, but let's not change the question. So let's keep this question only. So what we are getting 0.0259 10 to the power 19 divided by 10 to the power 16 minus 10 to the power 15, right? So 10 I can take common. Basically this can be replaced with 10 into 10 to the power 15 minus 10 to the power 15. So 10 to the power 15 is common. So 9 into 10 to the power 15. What you are getting 0.0259 into 10 to the power 19 divided by 9 into 10 to the power 15. So what you are getting 0.0259 0.0259 0.0259 divided by 9 into 10 to the power 4. So that would be 28.7 volt per centimeter. Okay. So this is your built-in electric field at x equals to 1 micrometer. Well and good. Fine. Now what I need to find? Built-in potential. So if I go by this formula, then calculation will be difficult. I will have to integrate. That integration will be a bit difficult. But I told you, I remember answer ln divided by, since it is the whole concentration, sorry, since it is the electron concentration, so one concentration divided by the other concentration. So value of Vt I already know 0.0259 ln concentration at 1 micrometer or concentration at x equals to 0. So what will be the concentration at x equals to 0? That would be 10 to the power 16. And what would be the concentration at x equals to 1 micrometer? What I mean to say is that, what is my N1? N1 is the concentration at x equals to 0. I could have taken the concentration at x equals to 1 micrometer as well, but I am taking the concentration at x equals to 0. What is that? Concentration at x equals to 0, that is 10 to the power 16. Right? And what will be the concentration at x equals to 1 micrometer? 1 micrometer means 1 micro. What does that mean? 10 to the power minus 4 centimeter. Right? So if I put 10 to the power minus 4 here, so 10 to the power 15, 10 minus 1, 9 into 10 to the power 15. 9 into 10 to the power 15. 9 into 10 to the power 15. So 10 by 9. 10 by 9 ln into 0.0259. So 27.28. No, sorry, 2.7. 2.72 millivolt. This is the answer we are getting. Isn't it too less? Am I doing some mistake? 10 by 9. What is the value of ln 10 by 9? 0.1, 2.72 millivolt. Answer will be positive only because this will be at the higher potential, this will be at the lower potential. So even if you had taken opposite, let's just say 9, let's just say if someone had solved in this manner, sir, I had solved in this manner, then sir, what you would have got? 9 by 10, so ln 0.9 you would have done 0.9 ln. So just try to do it in the calculator. So same answer you are getting, just negative answer you are getting, nothing difference is there. Are you able to understand this point? What I am saying is that, let's just say if you have put this upward and the other, this would have been upward for you, someone would have taken N1 as value of electron concentration at 1 micrometer. Then only difference would be of negative sign, nothing else. Only difference would be of a negative sign, nothing else there. Okay. So answer would have been same only. Answer would have been same. So you are getting minus 0.1, then you will multiply with 0.0259. So answer you are getting is 2.72, but in the negative. But you would see that, sir, x equals to 0 will be at higher potential. So my answer would have been positive only. So you would put a positive sign here. So forget about the sign, don't care about the sign, sir, positive sign, negative sign, don't care about that. Just solve the problem using the formula without looking at the sign, and then eventually you would see that we can apply positive sign or negative sign as per our diagram. So x equals to 0 will be at higher potential, x equals to 1 will be at lower potential. That's why here the positive sign would come and here the negative sign would come. Okay, well and good. So yeah, this question also we have solved. Now this question, first you will try it on your own. Very very high chance that you will not be able to solve it. Just just try thinking what is this 12 volt per centimeter. Okay, I am not saying that you have to solve it. It is a very good question. It will take 30 minutes to explain. I will take roughly around 30 minutes or 20 minutes for this particular question. So you you try doing it. If you are able to do it, very good. Like try everything about this question, that you let me know whether there is an external electric field or internal electric field, whatever it is, try everything and then try to solve it. From this question you will learn a lot of new things. Mathematics will also be used here. Okay, so try doing it. I have to take some break. I have to drink some water and then I will come back and we will solve this particular question. Yeah, thank you. Yeah, welcome back. So did you try this question? So first what we will do is that we will make the diagram. Constant electric field of 12 volt per centimeter is existing in the plus x direction for a n-type gallium arsenide semiconductor. So there is a semiconductor of n type and there is an electric field in the positive x direction. Let's just say this is your x equals to 0, then this would be your x equals to 50 micrometer. So in this positive x direction there is an electric field. Now sir, this is a built-in electric field, this is an external electric field, we don't know. Only we know that there is an electric field which is having a value of 12 volt per centimeter. Sir, built-in electric field, external electric field, we don't know, right? Let's read the question again. The total current density is constant and it is equal to 100 ampere per centimeter square. Let's just say if there was no external source, if there was no external source, if E external was 0, then the current density has to be 0. If E external was 0, then current density has to be 0, but J is equals to 100 ampere per centimeter square, which is non-zero. What does that mean? That means surely some external voltage source have been applied. Surely some external voltage source have been applied. So yes, external source is there. That's why there is a current. No, otherwise current would have been 0. Now because of the external source only you are getting 12 volt per centimeter. It is not necessary, because in the semiconductor as well built-in potential could be there. Let's just say because of the semiconductor you are getting electric field in this direction and I have applied the battery somewhat like this. Then what will happen? This built-in potential will be opposing this battery, because this battery will say that my electric field should be like this, but built-in potential will say that my electric field will be like this. So external and built-in both will be opposing each other. So you cannot say that sir 12 volt per centimeter is coming because of the battery. No, you cannot say that. You just know that total is 12 volt per centimeter. This is what you know. That's it. Nothing else you can comment. So total electric field is 12 volt per centimeter. This is what I know as of now. Now read the next line, very important line. A lot of students would have ignored this line, I know that. At x equals to 0, drift and diffusion currents are equal. At x equals to 0, what is the complete current? It is not a function of x. It is a constant current. At all the points, the current is constant, 100 ampere per centimeter square at all the point. But what they are saying is that at x equals to 0, the drift current and the diffusion current both are same. Both are same. At x equals to 0, drift current and diffusion current both are same. Both are same. Adding up both of them, you will get 100 ampere per centimeter square. If they were opposite in the direction, what I am saying that, let's just say drift current is in this direction and diffusion current is in this direction. If they were opposite in the direction and they are saying that both are equal, that means I am not sure whether they are talking about the magnitude or whatever they are talking about. Let's just say that by this statement I understand that they are talking about only the magnitude. So if drift current is 50 ampere, then diffusion current is also 50 ampere only. If I am saying that if both were opposite, then total current would have been 0 at x equals to 0. If both of the currents were opposite at x equals to 0, then total current would have been 0, but total current is actually 100 ampere per centimeter square. So what do you understand by that? I understand that actually both of the currents are added. And if both of the currents are added, what does that mean? That means both of the currents are in the same direction. That means diffusion and drift currents both are having the same direction only. Do you understand this point or not? What they are saying is, what I will write it down. If drift and diffusion current, if drift and diffusion currents were in opposite direction, then total current at x equals to 0 would have been 0 only. But total current at x equals to 0, total current at x equals to 0 is given as 100 ampere per centimeter square. That means drift current at x equals to 0, drift current at x equals to 0 is equals to diffusion current at x equals to 0 is equals to 50 ampere per centimeter square, and both in the same direction. So from here what you understand is that drift and diffusion currents both are actually in the same direction. So this is the conclusion that we have made. Now you let me know what will be the direction of a drift current. So what is the applied electric field? This is the eventually applied electric field. Like this is the total applied electric field. So let's just say there was an electron here. Because of this electric field, the electron will be drifting in this direction. And if it is drifting in this direction, then the direction of drift current would have been this. So this would have been the direction of drift current. I drift. Let me make it here. Since the applied electric field, this is your applied electric field, total electric field, not applied electric field, this is your total electric field. This is my total electric field. Since this is the total electric field, then electron would be drifting in this direction. And if electron is drifting in this direction, that means I drift would have been in this direction. And I know that the direction of I drift and I diffusion both are same. That means diffusion current will be in this direction as well. Did you understand this point or not? So if diffusion current is in this direction, that means where the electrons would have been diffused, electrons would have diffused in this direction, because if electrons have diffused in this direction, then only the diffusion current would be in this direction, no? So this would have been the diffusion of electrons. This I am calling as x equals to 0, and this I am calling as x equals to L, or x equals to 50 micrometer. Let's start again from the beginning. What I am saying, in the beginning I started reading the statement. I got to know that total current is non-zero. That means surely some external battery is applied. I don't care what kind of battery is applied, what is the potential of that battery, that I don't care. Now the next statement if I read, I get to know that the total current is constant, and and at x equals to 0, drift and diffusion currents are equal. Now they are talking about the magnitude or they are talking about the direction, I am not sure. So one thing I am pretty sure, that drift current is also 50 ampere and diffusion current is also 50 ampere. If if they were opposite, then they would have cancelled out each other and answer would have been 0. But at x equals to 0, the current is non-zero. So what I have written, if drift and diffusion current would be in the opposite direction, then total current at x equals to 0 would have been 0. But actually the current is non-zero. It is non-zero. And since it is non-zero, that means both of the currents are being added. That means drift and diffusion currents both are actually in the same direction. So both currents are flowing in the same direction. This is the conclusion I have made. Now again I came back to this question. On this semiconductor, the external field is this direction. The external field is in this direction. Total electric field is in this direction. So now how my electrons will drift? So electrons will be drifting in the opposite direction. That means the drift current would be in this direction. So if this is the direction of drift current, then I have said that drift and diffusion, both currents are in the same direction. And since they are in the same direction, so this is the drift current, so this would be the diffusion current. And if this is the diffusion current, then electrons would have diffused in this manner. Electrons would have diffused in this manner. What does that mean? That means that here the electron concentration would have been more, and here the electron concentration would have been less. Did you understand this point or not? Okay. So only on this analysis only the question can be framed. That where the electron concentration would be more, where it will be less. Only on this analysis only the question can be framed. Are you able to understand this point? Now let's see next thing. Mu n value is given. You need to determine the expression of electron concentration Nx. Expression of electron concentration we need to determine. So what is given? Complete current is given. I know that both of the currents will be added. That I know both of the currents will be added. Plus J diffusion. Both of the currents will be added. This is equals to 100 ampere per centimeter square. I know that everything is going in ampere per centimeter square. Let's write down. What would be your drift current? Sir, what about the built-in potential and anything? I don't care about the built-in potential now, because I know that total electric field I already know. So if my electrons are drifting, those electrons are drifting because of this field. So can I write down the expression? Yes. N Q mu E. N Q mu E. E total. Here in place of E, what I am putting? E total. And what about the diffusion? Q dn dnx by dx. Okay. Mu n value is given. Did they give the value of dn? No, 300 Kelvin they are talking about. So I need to find out the value of dn as well. So what would be the value of dn? Dn would be mu n by, okay, sorry, d is equals to uv. So mu n into vt. So value of mu n is given as 8 into 10 to the power 3. 8 into 10 to the power 3, and vt is 25.9 into 10 to the power minus 3. Okay, so you can solve it, you will get the value of dn. Et value you are having, mu n value you are having, q value you are having, this q value you are having, dn value also you are having. So you will get the expression. Let's write down the values. 100 is equals to, I have written down the values, so it will not take much time. 100 is equals to nx, the value of q is 1.6 into 10 to the power minus 19. Value of mu n is 8 into 10 to the power 3. The total electric field is 12 plus q is 1.6 into 10 to the power minus 19. dn value, this calculation I will have to do, so that I will do it, so forget about it, just remove this calculation. So dn is simply, just I am writing down, dn is simply mu n into vt. So I will just put the value mu n 8 into 10 to the power 3, vt value I already know, 0.0259 into dnx by dx. Okay, so you solve it and you will get the you will get the relation somewhat like this. How you will get the relation? So you solve all this calculation, you do this all this calculation. So dnx by dx plus 463.32 nx is equals to 301.64 into 10 to the power 16. So this is the differential equation I am getting. I will put this as A and this as B. So I just need to solve this differential equation, that I would be able to solve. Okay. So what I am saying, now the beauty will come. Okay. Now we need to solve the differential equation, and I know that a lot of people will be doing wrong here. So how will you solve this differential equation? Mathematics. Sir, I will be thinking of Laplace transform. So sir, what I can do, dy dx can be replaced with s, nx would be replaced with ns plus a ns. Sir, b was a constant value, so it would be b by s, and this step is wrong. This step is wrong. Why so? Because where you have considered the initial condition you forgot, no? Right? What I am saying is that if f of t is having a Laplace transform of f of s, capital F of s, then dy dt of ft, what will be its Laplace transform? S f of s. Is that correct? No. Minus f of 0. So similarly here s ns, what I am saying is that Laplace transform of nx is ns. Okay, this is what I am saying. Laplace transform of nx is ns. So s ns minus n of 0. So this n of 0 also I need to consider, right? N of 0, can you find out? You can surely find out. How will you find out? Just think about it. Just think, how will I find out the value of n of 0? Now this is my equation, or let's solve it more. What I can do is that s plus a will come common. So from here if I find out, so b upon s into s plus a plus n of 0, and don't forget about this s as well, because a lot of people will write down Laplace transform of b will be b only, b by s. A lot of time it happens with a lot of students. Laplace transform of 3 is 3. No, 3 by s. S upon s plus a. So how will I find out the value of n of 0? So now n of 0 I need to find out. What do I know? Drift current at x equals to 0 is equals to 50 ampere per centimeter square. So what is the drift current? N q mu e, right? So nx value at x equals to 0, q mu and applied electric field E total will be equals to 50. Q value you know, mu value you know, Et value you know. So from here you can get the value of n of 0. So your n of 0 would be coming out to be 0.325 into 10 to the power 16 atoms per centimeter cube. So this is your n of 0. Did you understand how did I calculate this n of 0? Because initial condition was given, no? If you need to find out the initial condition, then you need to use the initial condition. What is the initial condition given? That at x equals to 0, the drift current is 50 ampere per centimeter square. So at x equals to 0, drift current is 50 ampere per centimeter square. So you use this condition and you got the value of n of 0. Now you will put it here. Okay. So now it is just mathematics. Anyway, I will have to add a page. So now it would just be mathematics. So n of s would be value of b. Can I put, or shall I solve it? So you know how to solve these equations, right? Laplace transform and anything, you know how to solve it. So I don't think I need to put up the full equation. So just if you have studied signal system, then you would be able to solve it. If you have studied mathematics as well, then also you would be able to solve it. Even if you are not able to solve as of now, don't worry. After studying mathematics and signal system, you will be able to solve these equations. Okay, very simple it is. So nx is coming out to be 0.65 into 10 to the power 16 minus 0.326 into 10 to the power 16 e to the power minus 463.32x per centimeter cube. This is the answer that you are getting. Although this kind of calculation will not come in the examination, very rare chance. Even if it is coming, then you are not going to solve it in the examination hall. But I'm just telling that what is the depth of this question. And from this equation you get to know that at x equals to 0, the concentration will be maximum. At x increases, what will happen? This whole value will go down, right? At x equals to 0, the n of 0 will be minimum. This will be minimum. Why is that so? because as x increases, then this whole value will go down. If this is going down, then this whole value will go down. Something that is being subtracted, that is going down, that means this n of x will go up, right? If this value is going down, that means this whole value is going down. Or just calculate, no, just calculate what they are asking. They are asking, they would have asked electron concentration at x equals to 0 and at x equals to 50 micrometers. So what is the value of electron concentration at x equals to 0? That is 0.65 into 10 to the power 16. Sorry, no, from here I will subtract. So what I will get, I will put x equals to 0 here. So what I will be getting, 0.65 minus 0.326. So that would be 0.325, roughly around 0.325 into 10 to the power 16. Yeah. And if I put next, what they are asking, at x equals to 50 micrometer. So everything is going in centimeter only, ampere per centimeter square, everything is going in centimeter. So next, what they are asking, at 50 micrometer, at 50 micrometer. So you can call it at 50 into 10 to the power minus 4 centimeter, right? So what I will be getting, 0.65 into 10 to the power 16 minus 0.326 into 10 to the power 16 e to the power minus 463.32 into 5 into 10 to the power minus 3. So let's do this calculation. Have I written down the answer? No. 463.32 into 5 divided by 1000 plus minus e to the power into 0.326 minus 0.65. So roughly around 0.6178 into 10 to the power 16. This much concentration I am getting. So concentration at x equals to 0, concentration at x equals to 50 micrometer. This is the answer I am getting. Okay, next what they are asking, calculate that drift and diffusion current densities at 50 micrometer. So both of the components separately I need to find out. So what I would do, third, so drift current I need to find out at 50 micrometer. Or let's write it down as the expression of x. So what that would be, n q mu e total, n q mu e total, and here mu n. So nx I am already having, q value I already know, 1.6 into 10 to the power. Forget about it, I am not going to put the values, simply I will write down the answer. J drift I need to find out at 50 micrometer, right? So at 50 micrometer, what is the concentration I am having? At 50 micrometer, concentration that you are having is 0.6178 into 10 to the power 16, 1.6 into 10 to the power minus 19, mu n value 8 into 10 to the power 3, right? 8 into 10 to the power 3, and total electric field is 12. External electric field is 12. Where is total external electric field? That is 12. Okay, so what you are saying, 16, 3, 19, this and this will get cancelled out. 0.6178 into 1.6 into 8 into 12. So 94.90. What I am getting, 94.90 ampere per centimeter square. Let me check it again. 0.61 into 1.6 into mu n, that is 8 into 12. Yeah, 93.6, 0.6178 into 1.6 into 8 into 12, 94.9 or whatever it is, roughly around 94. This is what you are getting. So this is the value of a drift current here. So what will be the value of diffusion? You know that drift plus, you know that J total is equals to 100 ampere per centimeter square. So what will be your J diffusion at 50 micrometer? J diffusion at 50 micrometer, what that would be? 5.1, roughly around 100 minus 94.9, that would be roughly around 5.1 ampere per centimeter square. That's it. All good? All fine? So this is how I could have solved it. Calculation is complex, but you understood the conceptual part here, right? And just let me know one thing, what would be the direction of built-in electric field? This would have been the direction of built-in electric field. So now they are saying that total electric field is in this direction, which is 12 volt per centimeter. That means total electric field is going from x equals to 0 to x equals to 12, and built-in electric field inside going from x equals to 50 to x equals to 0. So what do you think, what will be the value of external electric field? That would have been greater than 12 volt or less than 12 volt. So external electric field would have been greater than 12 volt. It cannot be 12 volt, it cannot be lesser than 12 volt, it would have been greater than 12 volt. Why is that so? Because built-in electric field is opposing the external electric field. So you need to apply greater than 12 volt per centimeter so that this built-in electric field could be minimized. So external electric field would have been 12 volt per centimeter plus built-in electric field. If you want to find out the value of built-in electric field, that also you can find out. Okay, Nx value you are already having, Vt value you already know, and dnx by dx you can already do. So you can get the value of a built-in electric field as well. That would be a function of x. And similarly, you can find out built-in potential as well. So if you find out the built-in potential, then you can find out what should be the value of an external battery. Are you able to understand what I am saying? Basically, inside there would have been a battery like this, right? Positive side here, negative side here. So that's why this is the built-in electric field, no? Basically, externally you need to apply somewhat greater than 12 volt per centimeter. So there is something that is opposing. So if I find out built-in potential, if I find out a built-in potential, here if I find out built-in potential, can I find out the built-in potential? V built-in, what that would have been? Vt ln concentration at one point, concentration at the other point. So at both of the points I have find out the concentration. So 0.6178, 0.325, 0.6178 divided by 0.325, and Vt is 0.025. So let's find out this value. This is the built-in potential that I am finding. So 16.63, 16.63 volt. This is the built-in millivolt. Sorry guys. So I should write down 0.01663 volt. This is the built-in potential between what point? This is the potential between 50 micrometer, right? This is the potential between this 50 micrometer minus 0 micrometer. This is the potential between 50 micrometer minus 0 micrometer. This is the whole potential. Now you know that total external electric field is, total field is 12 volt per centimeter, right? Total field is 12 volt per centimeter. So what do you think, what would have been your total voltage? That would have been 12 volt per centimeter multiply with total length. What is the length of this semiconductor? Total length is 50 micrometer. 50 micrometer, that would be, so this and this get cancelled out. So 60 into 10 to the power minus 4. So that would have been 0.06 volt. So this is the total here, no, it is not the thermal voltage, it is the total voltage. So this would have been the total voltage that semiconductor is feeling. So semiconductor feels like that across me this much total voltage is applied. How much total voltage is applied? This is what semiconductor is feeling. Semiconductor is feeling that across me 0.06 voltage is applied. I hope I have done the calculation correctly. 50 micrometer, so 10 to the power minus 4, so 600, 10 to the power minus 2. Yeah, 6 into 10 to the power minus 2. And here what I was getting? 1.6 into 10 to the power minus 2. And here I am getting 6 into 10 to the power minus 2. 6 into 10 to the power minus 2. So just let me know what should have been the value of external battery. That would have been 6 plus 1.6. That would have been 7.6 into 10 to the power minus 2 volt. This would have been your V external. I should have applied a battery of 7.6 into 10 to the power minus 2 volt. Why is that so? Because I know that there is something inside that is opposing it. Inside there is a battery of this much opposition. What is that? That battery is 1.6 into 10 to the power minus 2. But total, your semiconductor is feeling that I am having 6 into 10 to the power minus 2 volt. In this direction. Direction is also given, no? This is the direction of electric field. If this is the direction of applied electric field, then you know that this would be positive, this would be negative. But inside there is a built-in electric field which is in the opposite direction. So they are opposing each other. So total electric field came out to be 12 volt per centimeter. Why is that so? Because total voltage your semiconductor was feeling that was 6 into 10 to the power minus 2. So externally how much you should have applied? Externally I should have applied 7.6 into 10 to the power minus 2 volt. And if they ask you what will be the external electric field, what would have been your external electric field? So that would have been 7.6 into 10 to the power minus 2 divided by 50 into 10 to the power minus 4 volt per centimeter. So you can solve it. 7.6 7.6 divided by 50 into 10 to the power 2. So 15.12 volt per centimeter. So externally I should have applied this much of battery, this much of electric field, so that it would have felt that, so that I should have applied a battery of 7.6 into 10 to the power minus 2 volt, because there is some built-in electric field which is in the opposite direction. Built-in electric field is in the opposite direction. So the external electric field and the built-in electric field are opposing each other. And since they are opposing each other, that's why the total electric field was 12 volt per centimeter. So from here I can find out the built-in electric field as well, because I have wrote down the this built-in potential for 50 micrometer. Built-in potential across these two terminals. Okay. Across the complete length, I have wrote down the built-in potential across the complete length, right? So across the complete length also I can find out the electric field as well, right? Okay then. So I hope you have understood the analysis here. Well and good. This part was not asked, but what I feel is that okay, like eventually in the examination, if they want to ask this particular part, then they have to give these values, right? In the examination, if they want to ask this particular part, they have to give these values, no? So in the examination, there is very rare chance that this kind of question would be coming, like this whole question would be coming. But in this 35 minutes of discussion, you would see that a lot of things we have discussed, and these things can be surely helpful in your examination. Okay, so you should be able to read the question very carefully, what they are saying, how the electric field is there, inside what would have been happening. So all these things cannot be discussed in theory. All these things could be discussed with the problem as well. It can discuss only with the problem. So this question was there and we have discussed it. So here our diffusion current gets completed. Now two more topics are there. One topic is minimum conductivity condition. Other topic is EK diagram. Okay. So these two topics we need to cover, but I need to take some break. So I will take the break and then we will study minimum conductivity condition. Okay, and this minimum conductivity condition will occur in p-type semiconductor only. So that also we will see. Do you remember the graph of conductivity versus temperature? Sorry, conductivity versus doping concentration. I told you that I am making it for n-type semiconductor only. The graph was like this. So for n-type semiconductor, this was correct. But in p-type semiconductor, something different will happen. So that we will see. Okay. So let me take some break and then I will come back. In that particular time, you revise this question again. That what all things are happening, sir, how everything is understood. Even if you are able to not do the mathematics, still it is fine. This is not the question of mathematics. This was the question of pure understanding. Okay. So let's meet in some time. Yeah, welcome back. So let's see this topic, which is minimum conductivity. So this is not related with diffusion current. This diffusion current has ended. Okay, whatever you want to learn in the diffusion current, that you have already studied. This is a different topic, minimum conductivity, very simple topic. Till this date in the GATE examination, they never asked question on this topic, but who knows, they may ask in the future. So what we were doing in the beginning of the lecture, in the beginning of lecture 1, we had an intrinsic semiconductor. The conductivity of intrinsic semiconductor was low. Since the conductivity of intrinsic semiconductor was low, what we did was we started doping this semiconductor. We could have doped it with donor atom, or we could have doped it with acceptor atom, right, to increase the conductivity. Do you really think that always the conductivity will increase? In case of n type, always the conductivity will increase, but in case of p type, something different could be there. So let's check that out. So for any kind of semiconductor, what is the formula of conductivity? N Q mu n plus P Q mu P, right? Because both of the currents, because of the electron and current because of the holes, both will be in the same direction. So conductivity will be added. Now you know there is something called mass action law. N into P is equals to Ni square. So the whole equation I want in terms of N only. So what I am doing is that sigma is equals to NQ mu n plus Ni square by N Q mu P. Now what I will do, I will find the value of N. What this is here, sigma is a function of N, right? Q is a constant value, mu n is a constant value, Q is a constant value, mu P is a constant value, Ni square is a constant value. Only variable is N, because N will be in our hand. Doping will be in our hand. How much doping do I do? That will be in my hand, right? So what I will do is that I will find the number of N such that sigma is minimum. What I am doing, my target is find N such that sigma is minimum. This is the target. To find the maxima or minima, what do you do? D sigma by dn is equal to 0. So if I do d sigma by dn, if you differentiate this with respect to n, so what will happen? Q and mu n are constant. Q mu n are constant. Differentiation of n with respect to n will be 0. Here Q mu p and Ni square are constant. Differentiation of 1 by n will be minus 1 by n square multiply with Ni square Q mu p, and that would be equal to 0. So value of n is coming out to be, Q and Qn will get cancelled out. From here you can see that value of n will come out to be Ni under root mu p by mu n. This is the value of n that you are getting. Similarly, if value of n you are having, then you can get the value of p as well. So what will be the value of p? Ni square by n. So what that would be? P would be Ni square by n if you do. So value of p will come out to be under root mu n by mu p. Now sir, you differentiated it and you equated it to the 0. Then how do you know that, sir, at this value of n or at this value of p, this is minimum? This could be maximum as well, no? What I am saying is that how could you tell that, sir, this value at this value of n or at this value of p, this is minimum? This could be maximum as well. Because if your graph is giving you differentiation equals to 0, so this could be maxima as well, this could be minima as well. You are not sure whether it is maxima or minima. For that you need to do the double differentiation. So you can do the double differentiation and you will get to know that it is minima only. So those who know mathematics, they would know that if I do the double differentiation, if I differentiate it twice, so here this term will be gone and you would see that double differentiation. Like just if someone is having the doubt that sir, why you are saying that at the differentiation you are getting minima only. You could get maxima as well, but actually this is minima only. When I do the double differentiation, what I get to know is that 2ni square divided by n cube q mu p I will be getting. And since this value will also be positive, this will be also positive, this will also be positive, this will also be positive. So here I can see that this double differentiation is coming out to be positive. If double differentiation comes out to be positive, that means this point was minima only. So at n equals to ni under root mu p by mu n and at p equals to ni under root mu n by mu p, your conductivity is minimum. So find out the electron concentration such that your conductivity is minimum. Answer would be ni under root mu n by mu p. Find out the hole concentration such that your conductivity is minimum. Answer would be ni under root mu n by mu p. These two are the answers there. Now just let me know one thing. You already know that generally our mu p is greater than mu n. So out of these n and p, which value will be larger? If mu n is generally sorry guys, mobility of electrons is greater than the mobility of hole. So generally mu n is greater than mu p. So out of these two, which value will be larger? Mu n is greater than mu p. So this value will be larger than this value. So from here what you can see is that for minimum conductivity, number of holes should be greater than number of electrons. This relation I already know, and here for minimum conductivity, value of p is coming out to be ni under root mu n by mu p, and value of n is coming out to be ni under root mu p by mu n, right? From here I can see that mu n is generally greater than mu p. That's why this p value is greater than n. And this condition is achieved in which kind of semiconductor? In intrinsic semiconductor? No. In n-type semiconductor? No. In p-type semiconductor. So minimum conductivity condition you can achieve in p-type semiconductor. What does that mean? That means that this I was having an intrinsic semiconductor. I was having. Then I started doping it. When I started doping it, I would expect that my conductivity should rise. Let's just say when there was no doping, this was my conductivity. But I would expect that just as I start the doping, my conductivity should rise. But what will happen is that initially it will decrease, it will reach at some point, and after that it will increase. So in p-type semiconductor, conductivity actually first decreases and then it increases. We will understand it by an example as well. Don't worry about that. Okay. So this is only for p-type semiconductor. So in p-type semiconductor, what you can say is that you can achieve the minimum conductivity condition. In n-type semiconductor, what will happen is that just as you have started doping, let's just say this was your intrinsic conductivity. Just as you started doping, always it will rise up only. What will be the nature? I don't know. Nature could go like this or whatever it is, but surely it will rise up only. It will not decrease. But in p-type semiconductor, what will happen is that first it will decrease and then increase. And we will see with respect to example, it will be more clear to you. So for the numerical purpose, what values you need to remember? This particular thing you need to remember, this particular thing you need to remember, and you got to know that the minimum conductivity condition can be achieved in p-type semiconductor. So this I will write down. Minimum conductivity condition can be achieved in p-type semiconductor. Okay. Now what will be the value of minimum conductivity? Basically, what was your sigma? Sigma was n q mu n plus p q mu p. For minimum conductivity, your n was coming out to be ni under root mu p by mu n, and your p was coming out to be ni under root mu n by mu p. Okay. So what would be your sigma minimum? So just put these values. Ni under root mu p by mu n into q into mu n plus Ni under root mu n by mu p into q into mu p. So what you are getting? This and this, what it will give you? Under root mu p mu n, and this will also give you under root mu n mu p. So what you are getting? 2 Ni into q under root mu n mu p. This is the value of your sigma minimum. Just remember these three expressions and you will be able to solve the problems. All good? All fine? Here I have written it can be achieved in p-type semiconductor or it could be compensated p-type semiconductor as well. Basically the condition is the number of holes should be greater than the number of electrons. This is the condition. Number of holes should be greater than the number of electrons. So this condition I can achieve in compensated p-type semiconductor as well, no? So compensated p-type semiconductor. So this minimum conductivity condition can be achieved in p-type semiconductor or in compensated p-type semiconductor. Okay. So so number of electrons value you should remember, number of holes value you should remember, and this minimum conductivity formula you should remember. Even if you forget it, you will be able to derive it very easily. Okay, so formula is 2 Niq under root mu n mu p. Okay, let's solve the question. A semiconductor is having intrinsic carrier concentration of 1.5 into 10 to the power 10 centimeter cube. The semiconductor is doped to achieve the minimum conductivity condition. So how will you dope it? So they have already given that ND value is 0. What does that mean? That means you are doping the acceptor atom, and it is pretty obvious as well, because you want to dope the acceptor atom only, then only you will get the minimum conductivity condition. So what they are asking, determine the required dopant concentration. That means you need to find out the value of Na. How much atoms you need to dope such that you achieve the minimum conductivity condition, and what would be the corresponding minimum conductivity. This is what you need to find. So for minimum conductivity, I remember the number of holes should be under root mu n by mu p. So I know that my holes should be 1.5 into 10 to the power 10. Mu n is 1300 divided by 500. Two point four two into 10 to the power 10. These many holes I require, and how many electrons I will have, because I know that mass action law will be valid. So how many electrons I will have. So forget about this formula. I will not remember this formula. I will just do Ni square by P. So what is my Ni square? 2.25 into 10 to the power 20 divided by 2.42 into 10 to the power 10. So what I am getting? Reciprocal into 2.25. So you are getting 0.93. into 10 to the power 10 centimeter cube. So what I have done is that I started doping that donor atoms. At some point of time, the number of holes became this much, the number of electrons became this much. At that particular point, my conductivity was minimum. So now looking at this particular expression, you would say that, sir, number of dopant atoms should be 2.42 into 10 to the power 10. Absolutely wrong. No, you need to apply the charge neutrality equation. No, charge neutrality equation. Don't do this kind of error. That, sir, number of holes are 2.42 into 10 to the power 10. What does that mean, sir? The number of dopant atoms should be 2.42 into 10 to the power 10. Absolutely wrong. No. This is the value of P that you have got. Are you able to understand that P was actually equals to Na by 2 plus under root Na by 2 whole square plus Ni square. right? So from here you need to find the value of Na. You need to find the value of Na. But solving this equation will be difficult. So I'm not going to solve this equation. What I will do, from where this equation was derived? From the charge neutrality equation. Charge neutrality equation. What did this charge neutrality equation said? Positive charge equals to negative charge. So Na will be a negative charge plus electrons will be equals to P plus Nd. Positive charge, positive charge. Here Nd is 0. So what does that mean? Na would be equals to P minus N. So what will be the value of P minus N? 2.42 minus 0.93. So minus 2.42. So 1.48. 1.48 into 10 to the power 10. What do you think? Is this the final answer? Is this the final answer? No. Why is that so? Because only 60% ionization is done. So if I give this much of dopant, if I put 1.48 into 10 to the power 10 boron atoms, if I put 1.48 into 10 to the power 10 boron atoms, so only 60% of this will give me hole. But I need this to be fully ionized. What does that mean? That means there should be some value of x. There should be some value of x whose 60% should be equals to 1.48 into 10 to the power 10. Are you able to understand this point or not? 60% ionization is done. What does that mean? That means only 60% of this guy will be able to contribute. But actually you require acceptor atom to be acceptor atom to be 1.48 into 10 to the power 10. That means this much acceptor atom you require. But useful acceptor atom are some x, only 60% of that. If I say that I will dope only 1.48 into 10 to the power 10 acceptor atom, then only 60% of this will be helpful. What does that mean? 1.48 into 0.6. So I will be getting only 0.88 into 10 to the power 10 useful atoms. Rest all the atoms will be wasted. But what I require, this is my requirement. This is my requirement. If this is my requirement, this number is my requirement. That means there should be some number x whose 60% should be 1.48 into 10 to the power 10 centimeter cube, right? Centimeter cube inverse. So this is not the final answer. What you will do is that 1.48 divided by 0.6. So 2.46. So value of x you are getting is 2.46 into 10 to the power 10 centimeter cube. There you go. So what does that mean? 2.46 10 to the power 10 atoms per centimeter cube doping will make sure that you achieve the minimum conductivity condition. Are you able to understand this point or not? So I was doping. At this point, I was getting the minimum conductivity. So there was some conductivity I was getting. Then I was doping. I got the minimum conductivity, and after this, it will increase. And let's check. What I want to check is that this particular scenario I am having. What I will check is that I will check the conductivity. I will check the intrinsic conductivity. First, what I will check? First, I will check the intrinsic conductivity. What I am gonna do is that this is the number of dopant atom I have got. This is the answer I have got. Next, what I need to find out the value of minimum conductivity. But first, let's check what was the value of intrinsic conductivity when there was no doping. When there was no doping, then what was the value of conductivity? At that point of time, this was your conductivity, right? This is your when no doping was there. No doping was there. When no doping was there. Okay, so what would have been the answer? 1.5 into 10 to the power 10 into 1.6 into 10 to the power minus 90. I don't think mu n value is given. Okay, it is given. 1.5 into 10 to the power 10 and q value 1.6 into 10 to the power minus 19, mu n mu p 1800. Okay, so you solve it and let's check what answer do you get. 1.5 into 1.6 1800. So 4.3 10 to the power 13, 4.32 into 10 to the power minus 5 Siemens per centimeter. This is the answer we are getting. This is the intrinsic conductivity. Now at this much of doping, how many number of electrons and holes you are getting? At this much of doping, these number of electron and holes you are getting, right? At doping of Na equals to 2.46 into 10 to the power 10. 2.46 into 10 to the power 10 atoms per centimeter cube. At this much doping, what is the scenario? At this much doping, your conductivity would be, at this much doping, what is the value of N? Number of electrons are 0.93 and 2.42. 0.93 into 10 to the power 10 per centimeter cube, and here number of holes were 2.42 into 10 to the power 10. So now you apply the formula of sigma, although it will be minimum only, so I am already putting minimum. So I already know NQ mu n plus PQ mu P. Okay, so you put the value, this value will be surely less than this, or I already know that what will be the formula, 2Ni Q under root mu n mu P. Okay, so either you put this value of N here, Q value you put, mu n value you put, P value you put, Q value you put, mu P value you put, you will get the same answer, whatever the answer that I am going to get from this particular formula. So what I would do is that 1.5 into 10 to the power 10 into 1.6 into 10 to the power minus 19 under root 1300 into 500. So 3 into 1.6 into, get out it, 13 into 5, 13 into 5, then you take the under root, so 10 to the power 2, then you take the under root into 1.6 into 1.5 into 2. So you are getting 3.38 I have got into the power 12, and yeah, 3.86 into 10 to the power minus 5 Siemens per centimeter. So this is the value of your minimum conductivity, and this was the value of your intrinsic conductivity. So even after doping you are getting lesser conductivity, and just try checking, let's just say Na value I have taken as 10 to the power 10 only. So you take the Na value as 10 to the power 10, then you calculate the value of number of electrons, then you calculate the value of number of holes, and then you again check the conductivity. You would see that this conductivity is coming lesser than this. So what really happened was, there was a intrinsic conductivity. From intrinsic conductivity you are going down, and then you will increase. After this point you will increase. What I mean to say is that, let's just say you take the doping value Na value as 3 into 10 to the power 10. What I am saying, you take the doping value 3 into 10 to the power 10. From there, then you apply this formula. Out of this 3 into 10 to the power 10, only 60% are useful. So first you will calculate the 60% of 3 into 10 to the power 10. Then you will put the value here. You will calculate the number of holes. Then you will calculate the number of electrons, and then you will apply this formula of conductivity. You would see that now the conductivity is coming more than this. So this is the minimum conductivity condition. After that, conductivity will rise up. So this phenomena happens only in p-type semiconductor. Are you able to understand this point or not? So usually I have seen that people remember the formula of minimum conductivity. They actually do not understand what is the meaning of minimum conductivity. So just this particular topic is saying that in p-type semiconductor, you have to, when you are doping, make sure that doping should be very larger than Ni. Because if you are doping just near to Ni. What was Ni? 1.5 into 10 to the power 10. And if I am doping 2.46 into 10 to the power 10, which is near to Ni only, then my conductivity is actually reducing. So I was doping to increase the conductivity, but actually it reduces. So in p-type semiconductor, I need to take care of this particular thing. Is that clear to you or not? Okay. So if any question can be framed from this particular topic, then it would be this particular question only. From here only every question can be framed. Just make sure that you are not going to find out the Na value from this particular formula. You will go to the charge neutrality equation. From there you would see that Na would be equal to P minus N. So value of P you would have already found, N value you would have already found. So from there you will calculate the value of Na. Is that clear to you? Okay then. So this topic is also completed. Next we need to study about EK diagram, but before that let's see some mathematics. Our next topic would be EK diagram, but before that I expect you to solve some question of mathematics. Can you draw the graph of y equals to x square? Yes sir, surely I can draw the graph of y equals to x square. As x increases, y also increases. So what kind of graph you will be getting? Sir, this kind of graph I will be getting. Y equals to x square, and since it is an even graph, so sir, this kind of graph I will get. Okay. Now the graph is y equals to x square. At x equals to 1, what is the value of y? Y is equals to 1. Now what about y equals to 2x square? At x equals to 1, what will be the value of y? That would be equals to 2. So what kind of graph you will get? This graph you will get, right? The graph will go like this or like this. The graph will be going like this or like this. It will be going like this, right? Why is that so? Because at x equals to 1, at x equals to 1, because at x equals to 1, at x equals to 1, this y equals to x graph, y equals to x square graph should give me value 1, but y equals to 2x graph, 2x square graph should give me value, higher value. So this value will be 2, but this value will be 1. Is that clear to you or not? Okay. 1, 2. So this graph is for y equals to 2x square. Now what I need to do, you need to find out double differentiation. So for the first case, what will be your double differentiation? For the first case, when y is equals to x square, when y is equals to x square. So here, what will be the value of? So first you differentiate, you will get 2x, double differentiation, you will get 2. And for this one, what you will get? So first differentiation you will get 4x and then you will get 4. So in this particular case, double differentiation is higher. Now if I ask you this curve and this curve, which graph is more curvy? This graph is more curvy or this graph is more curvy? This graph got the curve, no? So this is more curvy. So this is having more curvature. More curvature. Now in these two graphs, if I ask you y equals to 2x square or y equals to x square, which graph is more curvy? This graph is more curvy, right? Y equals to 2x square is more curvy. So y equals to 2x square is having more curvature. Y equals to 2x square is having more curvature. Curvature. Along with that, y equals to 2x square is also having higher value of double differentiation. Higher value of double differentiation as well. What does that mean? If you are getting higher value of double differentiation, that means you will say that your graph is having more curvature. High double differentiation means high curvature. Is that clear to you or not? From this particular question, only this conclusion is there. What is the conclusion? The conclusion is that the meaning of double differentiation is nothing but the curvature. That's it. Higher curvature means higher value. That's it. This is the meaning of this question. We will be using it somewhere. To understand our concept, we will be using it somewhere. That's why I took this question. I draw the graph of y equals to x square, y equals to 2x square. This is how the graph will go. I know that this graph is having more curvature. Y equals to 2x square is having more curvature. More curvature means along with that you can see that it is having higher value of d square y by dx square as well. So higher value of double differentiation means more curvature. That's it. Okay, I will be using it somewhere. Another question. you need to draw the graph of y equals to x square, y equals to minus x square. So what will be the graph of y equals to x square? Sir, the graph of y equals to x square we have already made. It will go somewhat like this. Now what will be the graph of y equals to minus x square? So the graph of minus x square will go somewhat like this. Okay. So this is the graph of y equals to x square. So this is the graph of y equals to minus x square. What this is? This is your concave upward. Concave upward. Can I call it concave downward? This graph is concave downward. What will be the value of double differentiation here? That would be 2. And what will be the value of double differentiation here? That would be minus 2. So if your graph is concave upward, then your double differentiation will be positive. And if your graph is concave downward, then your double differentiation will be negative. Understood? All fine? Okay. Sir, why you are teaching all this thing? It will be used somewhere. That's why. Otherwise, like when I teach the concept, in between I teach the mathematics, then it will be, you will feel like that, sir, why in between mathematics? But before teaching the concept only, I am teaching you the mathematics. Now the concept will feel like a cakewalk for you. So did you understand? This was the more important point. This was the most important point, I would say. If you understand this point, then surely the gate examination question you will be able to solve. That's for sure. That means higher differentiation means more curvature. Okay. Higher double differentiation. Higher double differentiation means more curvature. Now before starting our EK diagram, let's revise our chemistry that we studied in our class 11th 12th. So what de Broglie said? De Broglie said that if a particle is moving, it could be electron, it could be proton, it could be any particle, although proton doesn't move, but any moving particle will feel like a wave. Any moving particle will behave like a wave. What is the wave? This is like a wave. This is a wave. This is a wave. Now if there is some wave, so with respect to the wave, there are some parameters which we can define, and those parameters we study in EMFT. So there is one parameter that is known as wavelength. So the distance between the two peaks, this is one peak, this is other peak. So the distance between these two peaks is known as wavelength. So what is the wavelength? Distance between two peaks or crest of the wave. Crest means the bottom. Okay, so you just remember that the distance between two peaks is known as wavelength. And lambda is equals to h by p. This was the formula that was given by de Broglie. Lambda is equals to h by p, where p is the momentum and h is the Planck constant. So momentum, what is momentum? If mass m is moving with the velocity of v, then its momentum is given by p equals to mv. H is the Planck constant, whose value is 6.63 into 10 to the power minus 34 value joule into second. I was just thinking of the unit because E equals to h mu. So joule mu will be 1 by second. Yeah, joule into second. So you know what is the meaning of momentum? If m mass is moving with the velocity of v, then its momentum will be m into v. H is the Planck constant. Lambda is equals to h by p. What is wavelength? The distance between two peaks. There is another term that can be defined as just wait a second, guys. Yeah, so sorry for the interruption. Actually, I am having the cough, like serious it is. So I hope it is not creating much problem for you. Okay, when I am coughing, so I don't think that much of the sound is coming. I hope it is okay for you. Okay, so you guys can let me know in the comment section, like if this is troubling you. So what I would do is that I will not record at the time when I am not feeling well. Like currently, forget about it. Okay, let's go to our topic, which is wave vector. So there was a wavelength. With respect to wavelength as well, there is another term that can be defined as wave vector. When we study EMFT, we define it as phase constant, right? Beta equals to 2 pi by lambda. Beta is equals to omega by beta. Sorry, Vp is equals to omega by beta. So beta is equals to omega by Vp. So all these things we define in EMFT. In EMFT, you will understand the deeper meaning of wavelength. Okay, In EMFT, you will understand the deeper meaning of wave vector as well, or phase constant as well. But as of now, you just need to remember the formula k is equals to 2 pi by lambda. Okay. So if k is high, what does that mean? Lambda is low. If lambda is low, what does that mean? That means this distance is low. That means to reach from this particular point to this particular point, you will be taking lesser time because distance is low, no? Right? If k is high, that means lambda is less. Lambda is less, that means the distance between this point and this point is lesser. That means this wave is moving fastly. So what they have written, it is a way to describe the wave in terms of how fast it will oscillate in the space. So if k is higher, that means lambda is lower. If lambda is lower, that means oscillations are faster. So you don't need to think that, sir, what will wave vector represent? Wave vector is just representing that how fast the oscillations are. What is wavelength? Wavelength is the distance between two maximas, or you can say two peak values. And this relation that was given by de Broglie, that was lambda equals to h by p, and another relation you need to remember, k is equals to 2 pi by lambda. Okay, in EMFT you will study about all these things. You will study about the wave nature, everything in very detail. As of now, you just need to remember these two things. So de Broglie said that lambda is equals to h by p. So can I write down p is equals to h by lambda? Okay, p is equals to h by lambda. So let's do something. What I am doing is that p is equals to h by 2 pi. 2 pi by lambda. What I have done? Multiply and divided by 2 pi. So this h by 2 pi, h was a constant, 6.63 into 10 to the power minus 34 divided by 2 pi. So it would be another constant that I can write down as h bar. And what is 2 pi by lambda? 2 pi by lambda is k. So h bar is nothing but a constant only, which is equals to h by 2 pi. So don't worry about that. What is the final expression that you are having? P is equals to h bar into k. So from here you understood that momentum and wave vector are analogous to each other, right? So I will say that I am drawing the EK diagram, that means energy versus wave vector diagram, energy versus wave vector. But this diagram is known as energy versus momentum diagram. K is not momentum. K is not momentum. Who is the momentum? Momentum is P. But whenever I say EK diagram, in theory I will say energy versus momentum diagram. Is that clear to you? Are you able to understand this point? So in your mind, when I say K, momentum should come. Wave vector, forget about wave vector, anything. Everything is gone now. Only thing, this is the final conclusion now. P is equals to h bar k, where h bar is a constant. So whenever I say K, at that time wave vector should not come in your mind. At that time momentum should come in your mind. Is that okay for you? Right? So let's just say at one electron is moving with the velocity of v. Every particle have two kind of energy, kinetic energy and potential energy. Potential energy is coming because of its position, and kinetic energy will come because of the velocity. Like for me, let's just say I am sitting at a height of h, so and moving with the velocity of v. So my kinetic energy will be half mv square and my potential energy will be mgh. Classical mechanics, right? But what we are assuming is that this is a free electron. For two charge, let's just say one charge is q1, another charge is q2. If I ask you what is the potential energy of this charge q2, what that would be? So that would be k q1 q2 divided by r. This distance I am assuming as r. So potential energy of charge q2 will be k q1 q2 divided by r. But what I am assuming? I am assuming only a free electron. That means I am not taking effect of any other charge. The electron is free. That means its potential energy will be 0. I am not taking action into its potential energy. Are you able to understand this point or not? Right? So here I am writing down the energy of a free electron as half mv square only. Now some will have a doubt that, sir, why you haven't taken potential energy? Because I have assumed free electron. That means it is not there, it is not influenced by any other positive charge or negative charge. There is no influence on this particular electron. So it is a free electron. So energy will be half mv square. Now what I can do is that I will multiply by m here and then divide by m. So m square v square divided by m, right? So that would be half P square by m. So P equals to mv. What is P? P is equals to mv. So half P square by m. What is P? P is equals to h bar k. So what will be P? H bar k square divided by 2m. So what relation you are getting? E is equals to h bar k square divided by 2m. So this is the relation between E and K. What was our target? Our target was to find out the relation between E and K. So I started with E equals to half mv square. Then I know that from mv I can get the from mv what I can get? From mv I can get my momentum, right? So what I did, I multiply and divided by m. So this became P square by 2m. Since it became P square by 2m, then I know that P is equals to h bar k. So I can replace h square k square divided by 2m. So E is equals to h square k square divided by h bar square k square divided by 2m. Now what is the relation between Ek? If I want you to draw the Ek diagram, will you be able to draw the diagram? Y equals to some constant x square. E is equals to some constant k square. So Ek diagram will be a parabola. So if I ask you to draw the Ek diagram, then this is how the diagram will look like. Ek diagram will be a parabola. So this Ek diagram you are making for electrons. Now you know one thing, that for electrons energy increases in the upward direction. Electron energy will increase in the upward direction. So whole energy increases in the downward direction. So we have understood the Ek diagram for free electron. Electron means free electron only. So if I ask you to draw the Ek diagram for holes, how will you draw it? This is how I will draw it. Ek diagram for holes. In the negative direction, this is the E increasing K. So this is the upward direction. Now in the downward direction it will increase. So parabola only, but in the downward direction. Okay. So Ek diagram for free electron, Ek diagram for holes. So you would see that Ek diagram for holes will always be concave downward. Ek diagram for electrons will always be concave upward. Is that clear to you? Let me explain again. Lambda is equals to h by p, k equals to 2 pi by lambda, p is equals to h pi by lambda, h by 2 pi by lambda, h bar k. So p is analogous to k. Whenever you say wave vector, that means you are talking about the momentum. Okay. Now I want to find the relation between Ek. So half mv square, multiply and divide by m. So p square divided by 2m, p is equals to h bar k. So h bar square k square divided by 2m. So E is equals to h bar square k square divided by 2m. Right? The relation between Ek is simply parabolic. So E versus K diagram I have drawn for electron and holes. For electron, energy increases in the upward direction. So for holes, if I want to draw the diagram, I will make the parabola concave downward. This is concave upward, this will be concave downward. Is that clear to you? Everything is crystal clear, all good, all fine, right? Now what we need to find? We need to find the relation between effective mass and Ek diagram. This Ek diagram that I have made, how can I get effective mass out of it? So what I will do the double differentiation. If I do one differentiation, what I am getting? I am getting h square, 2k will come, 2 and 2 will get cancelled out. So h square by m. If I do another differentiation, what I will get? H square divided by m. So what you see here? What do you see here is that the value of m is h square divided by double differentiation. What does this double differentiation represent? What does this double differentiation represent? Curvature. So what do you see here is that m is inversely proportional to double differentiation of Ek diagram, or you can say that m is inversely proportional to curvature. So if your curvature is more, that means your effective mass will be lesser, and if your curvature is lesser, then your effective mass will be higher. So if I give you two diagrams and there I ask you which of the particle will have higher mass, will you be able to tell me? We will solve these kind of problems, don't worry. But as of now you have understood that higher curvature means lower effective mass and lower curvature means higher effective mass. So you will be able to understand that. We will solve some questions, but before that, let's find out the same kind of relation between velocity and EK diagram as well. So what we need to do, we need to find out the same kind of relation between velocity and EK diagram. So somehow I need to get velocity. How can I get the velocity? Velocity I can get from the momentum, right? So if I do one differentiation, d by dk, what I am getting? h square k divided by m, right? You agree to this point? Now I know that P is equals to h bar k and P is equals to mv as well. So V would be equals to, basically I need to get the velocity. This is my target. So in place of, yeah, so what I can see here is that d by dk, one h bar I am taking aside. So h bar k by m is equals to velocity. So what you are getting? Velocity is equals to 1 by h bar d by dk. So what do you see here? Velocity is proportional to the d by dk and proportional to the slope. So if I give you one EK diagram and I mark a few points and then I ask you at which point the velocity will be highest. So will you be able to tell me the velocity at which point the velocity of the electron will be highest? You will just see the slope. At the point where the slope is highest, at that particular point the velocity will be highest. So now we are going to solve all the questions of Niemann. Whatever the question are given in the Niemann, if they want to ask any question on EK diagram, then either it will be coming from this or this. That's it. From 3 questions only you will be able to understand every single thing about the EK diagram. So these are given in the Niemann and you will be able to understand. Let's revise whatever that we have studied. What we have studied, we started with lambda equals to h by v, p equals to h by lambda, then we find out the relation E equals to h bar square k square divided by 2m. Whenever I say momentum, at that time you need to think of k only. Then we draw the EK diagram for electrons and holes. Then we saw the relation. If I double differentiate it, then I can get the value of m. I got to know that m is inversely proportional to d square by dk. That means more curvature would result in lesser mass, okay, and lesser curvature would result in more mass. And the same kind of relation I could have find out for velocity as well. So for the velocity I just did one differentiation. So I got to know that velocity is proportional to d by dk. So it is proportional to slope. Now see this question. 2 possible conduction band diagrams are shown in E versus K diagram given in the figure. State which diagram will result in heavier electron effective mass. So here the word effective mass is written. Effective mass is written. But here I did not use effective mass. Here I did not put the star. Why so? Because this was a free electron, no? This was a free electron. But if the electron is moving in the conduction band, that means it will have to pass through crystal. Let's just say in the conduction band, if there is a free electron, so how it will move? It will move passing through the crystal, no? Like here it can be some impurity. This can be scattered, this can be vibrating as well. So here electron is not moving freely. It is going through this potential as well. It can have some negative potential as well. There could be phonon scattering as well. So here electron is not moving freely. So at that analysis, if I talk about the conduction band electron, and I write down the EK relation. So how will I write down the EK relation? I will write down the EK relation for conduction band electron in this manner. H square k square divided by 2 me star. Is that clear to you or not? I will use effective mass here. Why I am using effective mass? You understood? Because this is not the free electron. It is free electron but not completely free. Not moving very freely, right? Although we will draw the EK diagram for conduction band and valence band as well. That is our next topic only. So let's solve this question. These kind of questions only will come in your examination if it is coming from EK diagrams. So 2 possible conduction band are shown. For this particular question, this is the diagram. This is the diagram for this particular question, that is, and here this is the diagram for this particular question. 2 questions are there. EK diagram are shown. State which band will result in the heavier electron effective mass. So who is having more curvature? More curvature. So what I am saying is that d square by dk square for A will be more than the d square by dk square for B. That means effective mass of A will be lesser than the effective mass of B. Did you understand this or not? Okay, very simple. More curvature. How did you tell more curvature? Because this is more curvy. More curvature means lesser effective mass. So effective mass of A will be lesser than effective mass of B. One analogy I will tell you. Based on that analogy, you will be able to write down the answer very quickly. You don't need to think of EK diagram or anything. This is just a way to answer. What is the way? If I put a ball here and if I put a ball here, which ball will come faster? This ball will come faster, no? Because it is having more curvature. So if I put a ball here, this ball will come faster and this ball will come slower. So if some ball is coming faster, what does that mean? Its effective mass is low. That means the ball on curvature A is coming faster and ball on curvature B is coming slower. And if something is coming faster, that means its effective mass is low. So effective mass of A will be lesser than the effective mass of B. There you go. Just an analogy, just a way to answer in a quicker manner. If someone asks you in the interview, you will tell in this manner. That sir, this is having more curvature, then you can derive the things as well. Sir, I will do the double differentiation. Effective mass is inversely proportional to the curvature, inversely proportional to the curvature. So if it is having more curvature, then effective mass will be lower. If you want to answer in the competitive examination, you will just see that this ball will be coming faster. Since it is coming faster, that means it is having lower effective mass. There you go. What about this one, which is having more curvature? So effective mass of A here as well will be lesser than the effective mass of B, because here this is having more curvature, right? Very, very simple question. Okay, fine. Let's see the next question. At which of the position the velocity of the particle is higher? I am talking about the magnitude. Okay, I am talking about the magnitude. At which of the position the magnitude of the velocity, magnitude of the particle is higher, and what is the direction of the velocity? That also you need to tell. So what I know is that velocity is h bar 1 by h bar, or what? This is the relation 1 by h bar d by dk. So 1 by h bar d by dk. So just I can say that more slope means more velocity, right? So let's see at which point you will get the more slope. This point, this is the highest point, you will get the most slope here, and then this would be the second most. I am talking about the magnitude. Someone will say that sir, this is the negative slope. Magnitude of the slope, this is near to infinity, right? And this point is C and this point is A. So you can see that the slope at the point D is higher than the slope at point B, higher than the slope at point C, higher than the slope at point E. This is the order of the slope, right? C is at the higher. If you move on this curve, just let me know in one thing. If I am moving on this curve, my slope, if I go from here to here, my slope is increasing only, right? Here the slope is 0, then it will increase, at some point it will become infinity. So if I am walking on this particular curve, my slope will increase. And if I am walking from here to here, then also my slope will increase, but in the negative direction. Here the slope is 0 and here the slope will become minus infinity. Here the slope is negative only, negative, at some point it will become minus infinity. So on this curve as well, the slope is increasing only. Are you able to understand this point? If I go here, then it is increasing, but in the negative direction it is increasing. Although it is increasing only, no, magnitude is increasing only, right? Now I need to see the position of point C and A. I will see the position of point C. This is the position of point C and this is the position of point A. So although by looking at the diagram I am not able to tell that sir, this slope is higher, basically this value is higher or this value is higher. I am not able to tell looking at the diagram, but I know that C point is a bit above. Point C is a bit above than A. The position of point C is a bit above than the position of point A. So I know that if I work on this graph, then my slope will increase. Similarly here as well. That means if my point is at higher level, then my slope will be higher. So point C is at the higher level. Point D is at the highest level. Then point B, then point C, and then point A. So looking at the position of the points, I can tell that their slope will be higher because I know the nature of the graph. Are you able to understand this point? Someone will say that, sir, just by drawing these diagrams you cannot tell which slope is higher. You just put the you just made the slope at a particular point. Just looking at the slope at a particular point, I cannot tell which slope is higher. But you can think more. How you can think that if I move on the graph, that's why I said that for this particular graph, dy x square is always positive. That means when you are working on this graph, the slope is always increasing. The slope always increases. So yes, slope is always increasing, and in this direction as well, the slope is always increasing, but the sign is opposite. And what about the velocity sign? What about the direction of velocity? So here, direction of velocity for position D, it would be negative because slope is negative, no? The slope at point D and at point A. So from here I can say that velocity at point D is greater than the velocity at point B, is greater than the velocity of point C, is greater than the velocity of point A. And I am talking about the magnitudes. I am talking about the magnitudes. What I can see is that here MD and MC is having the negative slope and MA and MB is having the positive slope. Now they need to tell where the electron is moving. If electron is working in the positive x direction, then you say that at point D and C the velocity is in the negative x direction, and at point A and B it is in the positive x direction. Okay, is that clear to you? So basically, whatever the direction of position A and B is there, whatever the direction of velocity of position A and B is there, the direction of D and C would just be opposite. That's it. This is the only conclusion you can make. You don't know what is the velocity of electron, you don't know anything about the wave equation as well. Wave function also you don't know. So the only comment you can make that if A and B are having positive velocities, then C and D will have negative velocity. That means at point A and B, if you are looking towards plus x, then at point C and D you will be looking towards minus x. So if I am saying that VA and VB is positive, then VC and VD will be negative. If I am saying that VC and VD are positive, then VA and VB will be negative. Because wave equation I am not having. Right? Although wave vector will have the same direction as the wave propagation. So if this is happening in the positive x, that means I would say that at point A and B, the velocity will be in positive x, and at C and D, the velocity will be in negative x. Don't go too much into depth. These kind of questions have never come in the examination, and very rare chance that it will come. But if it is coming, you should have this idea. That's it. If you have this idea, then surely you will be able to solve that particular question. More slope, more velocity. If they talk about the direction, what you will see? You will see the value of slope. So slope at point A and point B are positive. Slope at point C and slope at point D are negative. So if they are positive, that means they are working in plus x direction. If they are negative, that means minus x direction. So in that manner you can tell. Okay, this you will say minus x direction, and this you will say plus x direction. Because just as I noticed that the direction of wave vector is in the same direction as the wave propagation. Now how did you tell that? This thing also you understand in EMFT, e to the power minus j k dot r. Basically the thing is, EDC is the subject that should be studied from the quantum mechanics part. In quantum mechanics, you will introduce the wave function, then you will write down the equation of wave function, you will solve that, you will solve the differential equation. From there you will get this relation. Then from here you explain the concept of electron and holes, and then you move to the conduction band and valence band. But actually we started from the conduction band and valence band. Directly I said that energy splitting will be there, this kind of waveform we will get. This will be the valence band, this will be the conduction band. And now I am explaining this EK diagram, because you cannot study that much in depth, right? In the examination, that much in depth is not coming. Till this date, they did not ask anything from EK diagram. Are you getting this point? Okay. So if they ask these kind of things only, they will ask. They will also make sure that it's not coming from the particle nature, particle and wave nature. Electron should be studied. First, you will study about the particle nature, then about the wave nature, then you will go to the quantum mechanics, and then you will come to the EDC. But you see the syllabus, in the syllabus, whatever the things that they have mentioned, they will ask from that particular point only. EK diagram is taught everywhere since it is related to conduction band and valence band. That's why I taught it. That's it. Nothing else. Okay. So this question you will be able to answer. Fine. You just need to, and this question is given in the Niemann book as well. Semiconductor Physics by Donald A. Niemann. So in that book as well, this kind of question is given. So from there only I took this question and I am explaining it here, because whatever that is given in the Donald A. Niemann, that is high probable for your examination. Okay. All fine. So this K is in the positive direction. So you would say that A and B are having positive slopes, so plus x direction, and C and D are having negative slopes, so minus x direction. Fine. Let's draw the EK diagram for our semiconductor. So in our semiconductor, you will have a conduction band and you will have the valence band. Whenever I talk about the conduction band, I always talk about free electrons, and whenever I talk about valence band, I always talk about the holes. So if I am making the EK diagram, how will I make the EK diagram? This is how I will make the EK diagram. Energy versus momentum. Looking upward. Why is that so? Because whenever I say conduction band, I talk about electrons. And now if I make the EK diagram, this EK diagram I have made for conduction band. Okay. And now if I make the EK diagram for valence band, then I will make it downward. I will make it downward. I will make it downward. Sir, why is that so? Because whenever you talk about the valence band, you talk about the holes. So electron energy will increase in the upward direction, hole energy will increase in the downward direction. Is that okay for you? All good? All fine? Now you see that conduction band, this is the energy only, no? This is the energy axis. Basically, this kind of graph it is there. This is the energy axis. But I have just made E and K. I did not make the full axis. Are you able to understand this point? Okay. So you can see that the minima of the conduction band and the maxima of the valence band is occurring at the same momentum. You would say, sir, this is wave vector. Wave vector and momentum are same thing, I told you, right? Because P is equals to H bar K. So whenever I say K, you should think about momentum only. So what I would say is that conduction band minima and valence band maxima is occurring at the same momentum, at the same value of K. So let's just say if there is some electron, if there is some bound electron here, if there is some bound electron here, and this bound electron wants to go to conduction band, So without changing the momentum, it can go into the conduction band. Say yes or no. Without changing the momentum, it can go into the conduction band. Without changing the momentum, it can go into the conduction band. And if it wants to fall back, I told you always there is generation and recombination process. Here electron hole pair are generated, and it may happen that it want to fall back as well. So if the electron is wanting to fall back, that means it will recombine with this hole. So when it is generating or when it is recombining, at both of the phenomena, it is not changing its momentum. So if the electron is going from valence band to conduction band or coming back from conduction band to valence band, in both of the conditions, momentum is not getting changed. And if this is the condition, then it is known as direct band gap semiconductor. So we were actually studying about direct band gap semiconductor. Okay. So when an electron is going from valence band to conduction band or coming back from conduction band to valence band, it doesn't have to change the momentum. That means conduction band minima and valence band maxima is occurring at the same momentum. So that kind of semiconductor is known as direct band gap semiconductor. Direct band gap. Okay, so this has been written here. Only just read about direct band gap semiconductor. What it is written? Conduction band minima and valence band maxima is at the same K value. Electron transition needs only photon. So this point I will explain. These points I will explain later on, but just you just read the point that conduction band minima and valence band maxima is at the same k. But now if your conduction band minima and valence band maxima is occurring at the different k, then what will happen is that then it is known as indirect band gap semiconductor. So this is your conduction band, this is your valence band. So your valence band maxima and conduction band minima is occurring at the different momentum. So what will happen is that, let's just say some electron wants to go from valence band to conduction band. So it cannot go like this. What it will do? What it will do is that first it will gain some energy, then it will reach here, then what it will do? It will change its momentum, it will change its momentum, then it will reach here, it will change its momentum, it will reach here, and then it will go to the conduction band. So from here the hole is made. So one electron wanted to go from the valence band to conduction band. So what really happened is that it gained enough energy, then it went to some particular energy level, then it changes its momentum. Let's just say here the momentum was k1, here the momentum is k2. So it made a change of k2 minus k1 momentum, and then it went to the conduction band. Now how the momentum can change? Let's just say I am having a mass of m and I am working with the velocity of v. So I am working with the constant velocity of v, right? If I collide with something, then only my momentum can change, no? Like if this is a flat road, I am working with a velocity of v, my momentum will never change. But if I collide with a small stone, then my velocity may change, and if my velocity is changing, then my momentum can change. So for the momentum change, collision is necessary, and whenever there is a collision, heat is generated. What I am saying, whenever there is a collision, heat is generated. What does that mean? That means if there is a change in momentum, that means heat will be generated. The same process, if the electron wants to recombine as well, then what it will do? It will go back, it will be coming at this particular energy level, then what it will do is that it will again change its momentum, and then it will fall back here to the hole. So for both generation and recombination, in both of the process, the momentum is getting changed, and momentum getting changed means there is a collision, and collision means heat is generated. So in indirect band gap semiconductor, heat is generated. So whenever an electron makes a transition from conduction band to valence band, heat and light both are generated. But in the indirect band gap semiconductor, since there is a change in momentum, so more heat is generated and less light is generated. Are you able to understand this point or not? In indirect band gap semiconductor, electron is not going directly, it has to change the momentum. Since it is changing the momentum, that means there is collision. Collision means there is heat. So in indirect band gap semiconductor, heat is generated, but in direct band gap semiconductor, light is generated. In both of the process, light and heat both are generated. In direct band gap semiconductor as well, in indirect band gap semiconductor as well, light and heat both are generated. But in direct band gap semiconductor, light is more, because here momentum is not changing. If momentum is not changing, what does that mean? Heat is not generating, right? So heat will generate, but in a very, very few amount. Similarly here, heat will generate in a very large amount, so light will not take much of effect. So most of the energy will be lost in the heat, and here most of the energy will be lost in the light. And light means photon. Light means photon, and heat means phonon. So when it makes the transition from conduction band to valence band, it will generate the light. So to excite this as well, I will give the light only. Basically, I will throw some light to my semiconductor, then what will happen is that electron from the valence band will go to the conduction band, and when the electron is coming from the conduction band to valence band, at that time it will generate light only, because there is no change in the momentum. So this is the line that has been written, that electron transition needs only one photon, and energy released mainly as light only, and that is known as photon emission. And one photon can excite only one electron. Although this point is not important, I am just telling that one photon will excite only one electron. Okay, and energy is mainly released at light only, so that's why we will use direct band gap semiconductor as LEDs, laser, and in all these kind of things. And examples are gallium arsenide and indium phosphide. Okay, so these are the examples. And what about indirect band gap semiconductor? So in the examination, how the question can come? Question will be coming from this theory. That's it. That in direct band gap semiconductor, direct band gap, you will see direct band gap. Okay, there is no change in the momentum. No change in the momentum. That means there is no heat. No heat means light. Light means photon. So in direct band gap semiconductor, photons will be generated. Photon emission will take place. Okay, photon means light. Light means it will be used in LEDs and laser. What all are the examples? Gallium arsenide and indium phosphide. These are the two examples. In indirect band gap semiconductor, conduction band minima and valence band maxima will occur at the different K. That means momentum change would be there. If momentum change is there, that means heat will be generated. Okay, so electron transition needs both photon and phonon for momentum conservation, and energy will be released mainly as heat, but light will also be released. If an electron is making a transition from higher state to lower state, then surely it will release some light. But here, more part will be of heat. Okay, so poor light emitters, so it will be used in electronics. Electronics means mostly we will make diodes, transistors. So for making diodes and transistors, we use indirect band gap semiconductor. Those are silicon, germanium. So what is the key difference? One liner key difference is direct band gap semiconductor means photons only, that means only light, and indirect band gap semiconductor means photon and phonon both will be generated, but mostly phonon will be generated. Is that okay for you? You will be able to remember direct, okay, direct transition, photon, indirect, change in momentum, momentum is collision, collision means heat, so heat is generated. That's it. This is how you need to remember. Now it feels like that, sir, compound semiconductors are direct band gap semiconductor and indirect band gap semiconductors are elemental semiconductors. But this statement is wrong. What is the correct statement? Correct statement is all elemental semiconductors are indirect band gap semiconductors, but all compound semiconductors are not necessarily direct band gap semiconductor. Okay, so very important line. Look, silicon, germanium, diamond, these are elemental semiconductor. Only one element is there, so all of these are indirect band gap. All of these are indirect band gap. None of them is direct band gap. Germanium can be used as a direct band gap semiconductor. Currently, research is going on this. Okay, so it can be used as a direct band gap semiconductor in some particular condition. But the bottom line is elemental semiconductors are indirect band gap semiconductors, and compound semiconductors are direct band gap semiconductors. This line is not true because you can see that these compound semiconductors, gallium arsenide, indium phosphide, gallium nitride, and cadmium, whatever it is, that is direct band gap semiconductor, cadmium telluride. And indirect band gap semiconductors are gallium phosphide, aluminum arsenide, and silicon carbide. So these are indirect band gap semiconductors. Okay, so only the points you need to remember. If first thing is that very rare chance that any question would be coming. If it is coming, then you will be able to answer. Now there is one semiconductor that is known as aluminum gallium arsenide. This semiconductor is known as aluminum gallium arsenide. So based on the composition of aluminum and gallium, it could be direct or indirect. So if x is equals to 0, the semiconductor is aluminum x gallium 1 minus x arsenide. If x is equals to 0, then what will be the semiconductor? Gallium arsenide. So gallium arsenide is direct band gap semiconductor. If x is equals to 1, then what will be the semiconductor? Aluminum arsenide. So that will be the indirect band gap semiconductor, right? But the typical value of x is 0.45. That means if x is less than 0.45, that means gallium is more. If x is 0.4, then gallium is more, aluminum is lesser. So if gallium is more, aluminum is lesser, that means it is more towards gallium arsenide. And if it is more towards gallium arsenide, that means it will be direct band gap. And if it is more towards aluminum arsenide, then it will be indirect band gap. A very famous example in EDC, sometimes question have been asked, that's why I wrote it here. But in GATE examination, again very rare chance that any question will be asked. So there is one semiconductor, aluminum gallium arsenide, based on the number of atoms, or I should not say number of atoms, based on the fraction of atoms. If gallium fraction is more, then it will be towards the direct band gap, and if aluminum fraction is more, then it will be towards the indirect band gap. So this slide is clear to you. Okay, there is nothing to explain in this slide. This slide is also clear to you because I have made the EK diagram for conduction band and valence band for direct band gap semiconductor and for indirect band gap semiconductor. In indirect, the electron is going indirectly. It will change the momentum and then it will recombine, or for generation as well, it will change the momentum and then it will recombine. So direct band gap semiconductor we have studied, indirect band gap semiconductor we have studied. So this lecture will end here. Okay, so this last part is not very important. Just whatever that has been written, just remember that particular part and you will be good to go. And in this EK diagram, these questions are important. This particular question is very important and this question is also very important. And whatever the relation that we derived here, these are also important. Okay, so if some question is coming from this particular topic, then it will be coming from this analysis only, whatever the analysis that we have done. All good, all fine. So we have seen semiconductor physics, 3 lectures we have done. In the next lecture, we are going to study about Fermi direct distribution. So we will comment on the probability of finding electron on a particular energy state. So that we are going to see in the next lecture. Okay then. So I hope you enjoyed the video. Thank you very much. Happy learning. Let's meet in the next lecture.